Imagine Earth as a single vast continent called Pangaea, joined edge to edge and wrapped by one immense ocean. Along the coasts, warm, shallow seas, deep inland, broad red deserts, and long seasons that test every living thing. The climate swings between heavy monsoon rains and long dry spells. Rivers carve through sandstone, then vanish into salt flats. Forests of conifers, cycads, and ginkgos gather where the water lingers. On land move early reptiles and the ancestors of mammals, and later the first small dinosaurs on open floodplains. Offshore, coiled ammonites drift while early marine reptiles hunt in clear water. No flowers yet. No birds. Just wind, dust, and a sky that cools quickly after sunset. This is Earth in the late Paleozoic and early Mesozoic, a world of one piece before the continents begin to pull apart. As always, I would love to know where in the world you are listening from and what time it is for you. Settle in, let your breathing slow, and imagine the map of Earth as a single piece once more. Picture Earth in the late Carboniferous, more than 330 million years ago. The planet is already restless, its surface divided into moving plates that glide on warm mantle rock. Across a span of tens of millions of years, these plates carry continents toward one another with the patience of geology. The speed is unromantic by human standards, a few centimeters each year, but relentless motion makes a continent cross an ocean in time. The result of that long migration was Pangaea, a single landmass that gathered nearly all of Earth's continents from pole to pole. The story of Pangaea begins with oceans that no longer exist. Between fragments that would become North America and Europe lay the Iapetus Ocean. Farther south, the Rheic Ocean separated Gondwana, a giant that contained Africa, South America, Antarctica, Australia, and India, from smaller northern continents. Subduction consumed those oceans. Where ocean crust sank, deep trenches formed, and volcanic arcs lit the horizon. When the last strips of Iapetus and Rheic were swallowed, the edges of continents met in slow collision, and mountains rose along the sutures like seams in stitched cloth. You can follow those seams today. The Alleghanian orogeny built much of the Appalachian core in North America as Gondwana pressed into Laurussia. The same collision raised the Variscan and Hercynian belts in what is now Spain, France, and Germany, and continued into the Anti-Atlas of Morocco. Farther east, the Uralian orogeny welded the East European craton to blocks that would lie near Siberia, creating the long spine of the Ural Mountains. These separate ranges, now scattered on different continents, are chapters of a single event. Their rocks record the crash. They show high-pressure minerals born at depth, slivers of ancient ocean floor caught between continents, and granites frozen from the last pulses of collision-related magmas. The fit of the continents remains one of the most intuitive clues. The bulge of eastern South America tucks against the Gulf of Guinea. The shape is not a coincidence carved by waves. It is the reflection of overlapping rock provinces and matching belts of deformation. Coal basins and granite provinces line up when you reconstruct the land masses. So do fossil zones that once formed continuous habitats. Paleontologists find Mesosaurus, a small freshwater reptile, in both Brazil and Namibia. This animal could not have swum across a salty ocean. Glossopteris, a seed fern with tongue-shaped leaves, occurs in thick Permian beds from India to South Africa to Australia. These plants spread across a single connected landscape. Climate left its signature on the rocks as well. Striations carved by moving ice run across ancient surfaces in South America, Southern Africa, India, and Australia. The marks point toward a shared center of ice. showing that these lands once clustered near the South Polar region. When geologists measure the magnetic orientation of iron minerals in old rocks, those paleomagnetic readings confirm the positions. The minerals aligned with Earth's magnetic field as they formed. When the rocks cooled, the alignment locked in like tiny compass needles. Together, the scratches of glaciers and the directions of magnetic grains let us rotate and slide continents back to the positions they held when Pangaea assembled. The mechanics of collision are methodical. Ocean crust grows at mid-ocean ridges and dies where it plunges under continents. That conveyor carries continents toward one another because continental crust floats rather than sinks. When the last ocean between them is gone, the leading edges crumple. Imagine two rafts drifting together in a pool that slowly drains. Where they meet, boards buckle and overlap. In a planet-sized version of that scene, sedimentary layers that once lay flat on quiet seafloors were folded into vast arcs and thrust faults, stacked slices of crust like cards. Metamorphic rocks record the heat and pressure of burial, and then a slow return to the surface as the mountains rose and the overlying load eroded away. As the sutures locked, Pangaea took on its famous shape. To the north sat Laurasia, a broad expanse stitched from North America, Greenland, and much of Eurasia. To the south lay Gondwana, still immense and complex. Between them and along the eastern margin opened a long seaway that would grow into the Tethys, an indented arm that admitted tropical waters. Everywhere else, the new supercontinent met water at steep coasts, and beyond those coasts wrapped a world ocean called Panthalassa. Ocean currents adjusted to this new geography. With most land consolidated, coastlines became fewer and longer, and the exchange between land and sea moisture changed. Those climatic consequences will be felt more strongly in the next chapter. But the seeds of that story are already present in the outline of the land. Mountain building was not a single moment. It was a drawn-out conversation between plates. The central and southern Appalachians carry evidence for several pulses that began in the earlier Paleozoic and culminated with the arrival of Gondwana. Europe records a similar sequence as arcs and microcontinents collided in stages before the final shove. Each pulse lifted new highlands and fed river systems that poured sand and mud into nearby basins. Those basins, trapped along the sutures, collected thick stacks of sediment that later hardened into red sandstones and shales. In places, the sediments preserve footprints of early reptiles wandering across mudflats and river bars near the rising mountains. The physics of the deep earth also played a role. As cool oceanic slabs sank into the mantle, they dragged the trailing plates and stirred convection. The changing balance of ridge push at spreading centers and slab pull at trenches nudged the continental rafts into alignment. The Wilson cycle, a pattern in which oceans open and later close as plates reorganize, is written in the timeline of Pangaea. Before Pangaea, there was Rodinia, an even earlier supercontinent. After Pangaea, the next cycle would pull it apart again. The dance is not random. It is the natural outcome of a cooling planet that sheds heat by moving its surface. To speak of Pangaea forming is to speak of geologic patience. From the first subduction of the Iapetus to the closing of the Rheic, from the early skirmishes that raised small arcs to the grand collision that stitched Africa to North America, the story spans more than 50 million years. During that time, life adapted to changing coastlines and rising mountains, while the chemistry of the oceans and the atmosphere adjusted to new patterns of circulation and weathering. By the early Permian, the supercontinent stood assembled. It was a world with familiar rules of physics but an unfamiliar map, a single landmass surrounded by a global ocean and laced with new mountain chains that would shape climate and evolution for the next 100 million years. When the last pieces of ocean crust slipped beneath continental margins and the sutures of collision cooled, the newly assembled continent began to behave like no landmass that had come before. All the great distances that once separated shore from shore were gone, replaced by an interior so vast that the sea sat far beyond the horizon for many lifetimes. A world that had been partitioned into island continents was now gathered into a single expanse that stretched from near the south polar latitudes to the northern temperate belts. Geography on this scale rewrites climate. The ocean is the great humidifier of the planet. Remove coastlines and moisture must travel farther inland. In the heart of Pangaea, that journey was often impossible. The result was a land interior ruled by extremes and a set of coastal belts whose seasons were powered by monsoons of uncommon vigor. The physics are simple enough to outline, yet intoxicating in their consequences. Warm air rises over sunlit land and sinks over cooler water. In summer, the land heats more quickly than the sea and draws moist air on shore. In winter, the pattern reverses and winds blow outward from a cooling continent. Multiply that contrast by a single supercontinent, and you obtain a planetary-scale monsoon that breathes along the edges of Pangaea every year. The coastal plains and the flanks of the new mountain belts took these rains and built rivers that swelled and shrank with the seasons. Floodplains spread like blankets of silt, and in low-lying lagoons, the warm, shallow waters grew carbonates and reefs that ringed quiet basins. Farther inland, the same atmospheric engine had the opposite effect. With little marine moisture able to survive the transit across thousands of kilometers, skies were often clear and rainfall rare. The interior of Pangaea was dry for years on end, and when rain did arrive, it came as storms that carved gullies and left braided fans of gravel and sand. Rocks are diaries of weather. In the interior, the pages are filled with wind. There are thick formations of cross-bedded sand that preserve migrating dunes, some the size of low hills. In North America, the celebrated Coconino sandstone records a Permian desert where winds sculpted vast dune fields and reptiles, left trackways that stitched across the faces of those dunes. In Europe, the Rotliegend sandstones lie beneath a blanket of marine salts and preserve rivers and desert winds from the waning stages of the Variscan Mountains. The striking thing about these deposits is their breadth. Desert sandstones are not local anomalies tucked behind a single mountain range. They extend across regions, evidence that aridity was a continental habit rather than a provincial quirk. Between dune seas lie sheets of red mudstone and siltstone that bear the color of oxidized iron. These red beds are the product of soils baked in the sun and flushed only occasionally by rain. Within them are calcrete horizons, where carbonates precipitated in the soil profile as groundwater rose and fell in a hot and evaporative climate. When you cut a slab from these rocks and examine it under a lens, you see the nodules and filaments of calcite that grew in place within ancient dirt, a signature of persistent dryness. Where seas managed to linger within the arms of the continent, they were rarely open to the world ocean. Restricted water bodies concentrate salt through evaporation. The late Permian Zechstein Basin across the lands that are now Germany, Poland, and the North Sea is the classic example. Layer upon layer of gypsum and halite record, repeated flooding by the sea followed by renewed isolation and evaporation. Each cycle formed a stack that may reach hundreds of meters in thickness, and these salts later flowed as soft rock under the pressure of burial, rising into domes that bend the younger strata above them. Engineers seek out these domes today because they are traps for oil and gas generated in the surrounding muds and limestones. The resource story is a reminder that our energy landscape is tied to the ancient geography of Pangaea. On the opposite side of the globe, in what is now the American Southwest, the Permian Basin preserves another facet of this marginal world. Along the rim of a deep basin, reefs of sponges and calcareous algae built steep walls known today as the Capitan Reef. To stand at the edge of the Guadalupe Mountains is to stand on a fossil reef that once looked into a deep, restricted lagoon, a quiet sea that rose and fell as climate and sea level pulsed. Mountains amplified contrasts in rainfall. The orogenic belts that stitched Pangaea together were not mere scenic backdrops. They were weather machines. The rising ranges forced moist coastal air to climb. As air ascends, it cools, water condenses, and rain falls on the windward slopes. The leeward sides sat in rain shadows, where descending air warms and dries. Rivers that began as wet season torrents on one flank dwindled to trickles or vanished onto dusty floodplains on the other. The great rivers still left their mark as tangles of channels that wandered across basins and cut terraces in older deposits. Where sediment overwhelmed the capacity of channels to carry it, alluvial fans spread at mountain fronts as cones of gravel and sand. On such fans, the footprints of early reptiles and the burrows of small animals are preserved, along with the imprints of raindrops and the cracked polygons of mud that dried beneath the sunday. The union of continents changed the chemistry of the atmosphere and the balance of carbon between air, water, and rock. Mountain building exposes fresh rock to weathering. When silicate minerals break down, they consume carbon dioxide and deliver ions to the sea where carbon can be locked into limestone. A young supercontinent with fresh mountains is therefore a carbon-hungry machine. Over long spans, this drawdown can cool climate. The story is complicated by other influences that push the thermostat in different directions. During the late Permian and earliest Triassic, vast volcanic provinces would vent greenhouse gases and heat the planet. For the moment, in the early history of Pangaea, the dominant signal in many regions was continentality, not global warmth alone. Put simply, being far from the sea dries you out regardless of the exact global average temperature, and that dryness shapes ecosystems. Plants told the tale in their own language. The Carboniferous had been a time of coal swamps in which tree-sized lycopsids and horsetails grew in waterlogged deltas and coastal plains. Much of that damp world disappeared as Pangaea expanded. In equatorial and subtropical belts of Laurasia, there was a shift towards seed plants that were comfortable in soils that drained more freely and in air that was seasonally short on moisture. Conifers and cordaites with waxy needles and tall, straight trunks are common in the record. Seed ferns, the glossopterids in particular, spread across Gondwana and formed forests that thrived in cool, temperate climates. Their leaves are found in thick beds that represent piles of litter on ancient forest floors. In some parts of Gondwana, coal formation continued through the Permian even as equatorial regions lost their great peat mires. Latitude mattered. The polar margins of the supercontinent could support peat forming wetlands, while the interior sat under sunday. In rare windows where plant cuticles are preserved, you can count stomata and infer the concentration of carbon dioxide in the air. These natural sensors confirm that the breath of the planet changed as the mountains rose and as the pattern of rainfall reorganized. Animals adapted with equal ingenuity. The decisive evolutionary invention for life on land was the amniote egg, a portable watery world surrounded by protective membranes and often a leathery or calcified shell. With this innovation, vertebrates no longer needed to return to ponds and streams to reproduce. They could roam the interior deserts and lay their eggs in sheltered places beneath shrubs or within shallow burrows. The early Permian shows the success of this strategy. Synapsids such as Dimetrodon and Edaphosaurus moved through dune valleys and across river flats. These animals are often described by their sails, tall spines that supported a skin membrane along the back. Whether those sails were for thermal regulation or display or both is still debated, but the very appearance of such structures speaks to life in an environment where mornings were cool and afternoons hot, where warming quickly or advertising vigor had value. Later, synapsids gave rise to therapsids that included tusked herbivores with beaked mouths and fleet predators with saber-shaped canines. Their bones are most famously gathered in the Karoo Basin of South Africa, a Permian and Triassic archive where species succeed one another through time as the climate shifts and as extinction pulses remade communities. On the reptilian side of the family tree, Pareosaurs lumbered as armored herbivores, and early archosaur relatives explored the roles of mid-sized predators. Amphibians persisted along rivers and in lakes, but their reliance on water constrained their range in a continent that did not guarantee reliable rains. Even the small denizens of the air and the undergrowth betrayed the new climate. Insects are sensitive to oxygen and humidity. The swollen dragonflies of the earlier Carboniferous became rarer as oxygen levels declined from their earlier highs and as different plant communities reshaped the food web. The Permian insect fauna includes beetles, cockroaches, and early relatives of modern groups whose mouthparts and life cycles suited a world with widespread dry seasons and frequent fires. Charcoal is abundant in many Permian strata. Fire needs fuel, oxygen, and a spark. In dry seasons, fuel cures and lightning provides the spark. On plains where conifers and seed ferns dropped resin-rich litter, fires would have raced across the ground and licked into the lower branches, opening cones and turning leaves to ash. The record of charcoal tells us that Pangaean ecosystems were not only arid but also flammable, and that plant lineages were selected for traits that allow survival through fire, whether thick bark, serotinous cones, or the ability to resprout from protected buds. The coasts of Pangaea were no less full of narrative. Where the monsoon breathed most deeply, the seasonal cycle wrote vivid patterns into the deposits of lakes and lagoons. During the wet season, rivers carried suspended clay into basins and laid down dark laminae. In the dry months, evaporation concentrated salts and lighter sediments filtered into quiet water. These couplets stack to form varves, pairs of layers that together mark a single year. Climatic beats of longer period are encoded as bundles of couplets, whose thickness waxes and wanes with orbital cycles that modulate the strength of seasons. In marine settings along the margin of the young Tethys, carbonate platforms grew in warm, clear water, building banks and reefs filled with the skeletons of sponges, bryozoans, and algae. Shelves sloped into deeper basins where fine mud accumulated and where periodic incursions of oxygen-poor water left faunas stressed and simplified. The map of such facies, belts, circled the supercontinent and shifted with sea level as ice advanced and retreated at high latitudes. Ocean circulation adjusted to the absence of many old gateways and to the presence of a single giant landmass. Panthalassa was a world ocean, yet it was not a featureless bowl. Winds drove currents that hugged the edges of Pangaea and swept equatorial waters westward. Where cold waters rose from depth along continental margins, they fertilized surface waters and fed rich blooms of plankton. Those blooms drifted and sank, carrying organic carbon to the bottom, a slow rain that built black shales in basins where oxygen was low. The carbon pump of the ocean was intimately tied to weathering on land and to the delivery of nutrients by rivers that surged in the wet season. When continents are gathered into a single mass, the contrast between the few very long coasts and the immense interior means that the global exchange of carbon and nutrients is conducted through fewer gates. That fact makes the system more susceptible to bottlenecks. A change in wind belts or in sea level can reorganize currents on a planetary scale. The daily experience of life on Pangaea would have been one of place and contrast. Imagine standing in the shade of a conifer on the leeward side of a mountain range, as noonday heat rattles, cicadas, and dust devils sway along a dry arroyo. There would be animal life adapted to this rhythm. Burrowing was common. Many reptiles and synapsids took shelter below ground where temperatures fluctuated less and humidity remained higher. Scales and skin prevented water loss. Concentrated urine and dry feces conserved precious moisture. Grazers browsed on tough leaves and seeds rather than on soft submerged plants. Predators learned to hunt at dusk and dawn when temperatures were less punishing and when the scent of their quarry carried in still air. Move the scene to a coastal plain, and the picture changes quickly. Clouds pile on summer afternoons, and a hard rain falls, drumming on broad leaves and silencing dust. Rivers become chocolate torrents. Estuaries smell of salt and wet vegetation. In these zones, amphibians flourished, and the young of many reptiles and synapsids grew quickly on a yearly pulse of food. The New World was not uniformly hostile. It was varied and patterned, and those patterns set the stage for what would follow. Environmental gradients encouraged diversification. Along a single river that ran from a wet mountain front to an arid basin floor, there would be niches spaced like beads on a string. In the Permian and Triassic, that string was repeated across Pangaea, and life responded by dividing itself among specialists. Some lineages took the path of endurance, evolving physiologies that wasted little water and that tolerated heat. Others exploited seasonal abundance and hid during the long, lean months. When the greatest extinction in Earth history arrived at the end of the Permian, these pre-adaptations influenced which clades survived the purge. Those details belong to a later chapter. What matters here is that the union of continents created new rules of living, and the biosphere learned them quickly. There is a quiet beauty in the record that allows us to reconstruct this world. On the underside of a sandstone slab, a geologist may find the trails of arthropods that scuttled across damp sand during a brief shower and then baked into permanence under the next day's Sunday. In the middle of a thick stack of red beds, there may be a lens of gypsum crystal fans that grew in a playa lake as water evaporated and saturated brine crystallized on the lake floor. A reef margin now perched in desert air preserves the outlines of ancient sponges. A coal seam in a Gondwanan basin tells us that a temperate wetland persisted beneath a cool sky, even as deserts expanded nearer the equator. Every such piece is a line in the long paragraph of Pangaea as a functioning planet. The final measure of this new world is felt in time. After the collisions quieted, Pangaea remained assembled for tens of millions of years. Through that span, climates breathed and ecosystems shifted, but the essential frame of a giant interior and active monsoon margins persisted. The very persistence of this pattern taught life to make good use of it. Forests walked back and forth with the seasons along river corridors. Dune fields migrated and sometimes were arrested and stabilized by vegetation as rainfall patterns shifted for a few thousand years. Lake basins filled and dried, leaving shorelines like nested steps. The supercontinent was not static, it was responsive, yet it retained identity. The next act would test that identity through the greatest biological crisis the planet has known, and through the first stirrings of a fracturing crust. Before those changes, the stage was set by a landmass that had no equal, and by an atmosphere and ocean forced to negotiate with it. The Permian opens on a planet whose map has been redrawn by patience. By the time we step into this chapter, the sutures of collision that built Pangaea have cooled enough to become landscape rather than catastrophe. To the east lies the long indentation of the Tethys. Everywhere else, the land meets the global ocean of Panthalassa in a cliff of continental presence. The supercontinent stretches from high southern latitudes well into the north, a single labyrinth of mountain belts, plateaus, basins, salt flats, and dune seas. Such geography is not a neutral canvas. It reorganizes the most basic exchanges of water and heat between air, land, and sea. In the earliest Permian, glaciers still linger over parts of southern Gondwana. Their scratches are etched into bedrock from South Africa to Australia and India, a fading memory of a colder Earth. As the period progresses, those ice sheets retreat and vanish. Their withdrawal does not herald a gentle Eden. It reveals a continent where the interior is set far from the softening breath of the sea. The prevailing mood will be dryness, interrupted by the theatrical entrance of seasonal storms along the coasts and mountain fronts. The physics that govern this mood are straightforward and profound. Land warms and cools more quickly than water. In summertime, the heated continent draws moist air from the seas, and in winter, the cooling land sheds air back toward the coast. This is the monsoon, and on the scale of Pangaea, it is a planetary instrument. Along the edges of the supercontinent, the summer monsoon breathes moist air inland. Rains fall in powerful bursts. Rivers rise and braid across floodplains, and in shallow embayments, the water turns warm and clear enough to encourage reefs. Then the breath reverses. Dry season winds sweep back toward the ocean, and the same plains bake under a bright sun until the next cycle. Move inland by 1,000 kilometers, and the tune changes again. Whatever moisture penetrates this far is spent on the flanks of mountain ranges, and the rain shadow beyond is a world of red soils, sparse vegetation, and long horizons. The day can be a furnace, and the night can cool enough to crust a dune with frost. Travelers would move by flood channels and the shores of shallow lakes that appear and vanish with the seasons, and by the bones of old rivers now filled with sand. The rocks of the Permian preserve this choreography with an attention to detail that rewards patient reading. The great desert sandstones of western Laurentia are built of wind. The Coconino, Decelli, and Cedar Mesa formations, among others, are tapestries of crossbeds where inclined layers sweep upward in grand arcs and tangles. These geometries are the slip faces of dunes, rebuilt grain by grain as sand avalanche down a leeward slope under a relentless wind. Trace fossils enliven those slopes with the tracks of reptiles and arthropods that climbed, slid, and corrected their footing on steep faces before their trails were fixed by the next gust and the next thin film of dew. Between these Aeolian giants lie broad fields of red siltstone and mudstone that record floodplains and playas. The red is the color of oxidized iron, a chemical signature of soils repeatedly aerated and dried. Within these red beds there are horizons of calcrete, an accumulation of carbonate nodules and filaments grown in the soil itself as groundwater rose and evaporated under strong Sunday. Every calcrete band is a quiet testimony to a landscape where water was intermittent and precious. Where arms of the sea extended into the continent and found themselves isolated by sandbars or subtle shifts in sea level, evaporation became a geologic engine. The late Permian Zechstein Basin of northern and central Europe was such a place. Over repeated cycles, seawater flooded in, became trapped, and concentrated its dissolved salts until minerals began to precipitate. The sequence is almost ceremonial. First gypsum, then halite, then more exotic salts, each forming in turn as the brine thickened. The result is a stack of evaporites hundreds of meters thick that later flowed like cold honey in the subsurface. The softer salt rose into domes, warping the younger layers above into gentle arches and traps that would one day hold oil and gas. On the far side of the ocean, along the ancient margins of what is now Texas and New Mexico, a different record speaks just as clearly. The Capitan Reef grew along the rim of a restricted basin, a steep wall of sponges and calcareous algae that faced deep, quiet water. Today, those reefs stand in desert air as the Guadalupe Mountains. Their vertical cliffs are the frozen crest of a Permian reef, complete with channels, talus slopes, and the intricate textures of colonial organisms that once filtered warm, clear water. Mountains in the heart of Pangaea were more than landmarks. They were switchboards that routed wind and rain. The highlands thrown up by earlier collisions still scraped moisture from air masses that tried to cross them. On windward slopes, the monsoon rains fell hard and often. Rivers leapt with boulders and gravel. At mountain fronts, alluvial fans spread out as cones of cobbles and sand where channels could no longer confine the flow. On leeward slopes, the story inverted. Descending air warmed and dried. The same rains that fed a tangle of ever-shifting streams on one side could fade into dust on the other. Basins trapped along the sutures between old terrains filled with thick packages of sediment carried off the mountains in pulses. Within these packages there are intervals of quiet water deposits, thinly laminated clays that record lakes which persisted long enough to lay down varves. A pair of layers makes 1 year. A bundle of pairs waxes and wanes with the slow beats of the planet as its orbit and tilt modulate the strength of seasons. The Permian is full of such rhythms. They are the fingerprints of climate written in mud. Climate is also written in the breath of plants and in the ash of fires. During the Carboniferous, oxygen content of the atmosphere had climbed to heights that supported dragonflies with wings like dinner plates and damp coal swamps, so productive that their peat became the economic backbone of later ages. Through the Permian, as coal swamps contracted in the equatorial belt of Pangaea and as plant communities shifted, oxygen appears to have declined from those earlier highs. The numbers are reconstructed from the chemistry of air bubbles trapped in salt and from the structure of fossil leaves whose stomata betray the balance of gases in the air in which they grew. The decline is not a collapse. It is a settling from exuberance toward a composition more familiar to us. The ecological consequences seem to include a reduction in the extreme sizes of certain insects and a change in fire behavior. Charcoal becomes abundant and widely distributed in Permian strata. Fire marks the ground where seasons dry litter enough to carry flame and where lightning under a dry sky provides a spark. Many conifers carry resin-rich wood and cones that respond to fire by opening or by surviving heat. Forests that live with fire learn to shed branches, to thicken bark at the base, to grow in mosaics that resist crown fires, and to regenerate quickly after a burn. The widespread presence of charcoal in Permian deposits tells us that such lessons were common. Plants themselves are among the most eloquent narrators of Permian life. The fen and forest of the Carboniferous gave way across much of equatorial Pangaea to communities that conserve water and tolerate heat. Early conifers such as Walchia stood with narrow leaves and tall straight trunks, their wood adapted to dry air. Cordaeites, with strap-like leaves borne on tall stems, still occupied some wet lowlands and coastal plains, but their domain was shrinking. Among Gondwanan lands, seed ferns of the glossopterid group carpeted temperate valleys and uplands with broad leaves that fell in drifts, later to become coal in basins, where water and sediment sealed them from decay. These were forests of a different character than the peat swamps that preceded them. Roots probed deeper. Soils matured under alternating wet and dry seasons. And the forest floor carried a litter that crackled underfoot during drought. Ginkgo relatives and early cycads appear in the fossil record and contribute to an image of forests that are more open and more evergreen than the often saturated worlds of the Carboniferous. Pollination still depended largely on wind, but the architecture of cones and seeds was changing in ways that would echo through the next 200 million years. Animals kept pace with these new landscapes. The amniote egg made the interior of Pangaea accessible to vertebrates by freeing reproduction from the shorelines of ponds and lagoons. Early in the Permian, Synapsids were the dominant large land vertebrates across many regions of the supercontinent. Dimetrodon prowled along river margins and across dune-backed flats, a predator with a deep skull full of slicing teeth and a tall sail of spines that may have helped it warm in cool mornings or display in confrontations. Herbivorous Edaphosaurus moved more slowly through the same habitats, its own sail decorated by crossbars that anchored muscle and skin. The living community was richer than these museum favorites. Small insect-eating synapsids, slender reptiles suited for climbing and sprinting, and armored parareptiles such as bolosaurids shared the floodplains. Amphibians persisted along the waterways as sprawling temnospondyls with wide heads and gaping mouths that could engulf fish and unwary juveniles of other species. Fossil trackways from the American Southwest, from the red beds of the Karoo, and from Europe capture their movement with a charm that anatomy alone cannot supply. A row of footprints breaks stride and arcs aside at an angle, and we imagine the animal hesitating, then veering, perhaps at a sound or as the sand slumped away beneath a forefoot. By the Middle and Late Permian, the synapsid story turns a page. Therapsids flourish. This is the lineage that will one day yield mammals, and in the Permian it is already experimenting with anatomy that looks surprisingly modern in function. The limbs move a little closer to the body. The chest deepens. The jaw joint becomes more complex, and the teeth differentiate into incisors, canines, and postcanines. In the Karoo Basin of South Africa, bone beds record the rise and fall of entire faunas through time. There are tusked herbivores like the dicynodonts, whose toothless beaks and powerful jaw muscles made short work of tough vegetation. There are bulky dinocephalians whose bones were sculpted to hold massive muscles and whose heads carry thickened arches that may have been used in ritual combat. There are sleek gorgonopsians with long canine teeth and a predator gait that suggests speed and precision. These communities are not isolated. Comparable assemblages appear across Russia and into China, each with its own cast of genera that played similar roles under different skies. The presence of such animals argues for landscapes where drought was frequent but not absolute. Grazers and browsers need corridors of growth along river margins and flood basins. Predators need cover and water for their prey. The interior of Pangaea was harsh, but it was also dynamic and patchy. Life can make a great deal out of patchiness. Away from the land, the seas that lapped Pangaean coasts carried their own signatures of a changing world. On shallow shelves along the margins of the Tethys, warm and clear water hosted reefs built by sponges and calcareous algae. Shelves sloped to basins where oxygen sometimes faltered. In such waters, organisms that could tolerate low oxygen or that depended on opportunistic strategies thrived. Organic matter sank and accumulated as dark shales. These shales bear witness to episodes when circulation and climate reduced mixing and limited the reach of oxygenated waters into the deep. They are the marine analogues of the inland evaporites and red beds, products of a planet whose circulation was channeled and focused by the geography of a single supercontinent. The chemistry of the sea responded to the pace of weathering on land. As bare mountain faces crumbled under sun and storm, ions poured into the oceans. Carbonate sedimentation waxed and waned with those inputs and with the ecological fortunes of the organisms that precipitated calcium carbonate into skeletons and reefs. Seasonality under the monsoon belt left a quiet but persistent mark on lake basins and coastal plains. In many Permian lacustrine deposits, thin pairs of laminae record a single year of sediment fall. The thicker, dark layer is a wet season delivery of clay and organic matter. The thinner, pale layer is a dry season curtain of silt or the chemical precipitation of carbonate as evaporation concentrates ions in shrinking water. Count 100 pairs, and you have a human lifetime. Count a few thousand, and you are beginning to feel geologic time in your fingertips. Superimposed on these annual beats are longer modulations tied to cycles in Earth's orbit and axial tilt that change the intensity and timing of seasons. These longer rhythms are recorded as bundles of varves that grow thicker and then thin as the strength of the monsoon waxes and ebbs. Such records allow us to pace ancient climates with a precision that can be startling. We can say not just what the climate was, but how it pulsed. The Permian interior was not a uniform desert. It was a mosaic of dry places and temporary abundance. Across the basins trapped along Pangaea's sutures, one may find lens-shaped deposits of lake muds within stacks of red beds, the signature of short-lived lakes known as playas. When seasonal or rare multi-year wet periods filled them, these lakes hosted brine shrimps, small fish, and mats of microbes that bound the sediment surface. When they dried, the mud cracked into polygons. Salt crystals grew in the top few centimeters and later redissolved and reprecipitated as the next flood arrived. The resulting surface textures are preserved beneath thin sand sheets that blew in from nearby dunes. A geologist can walk along the cliff face of a Permian outcrop and see this alternation at a human scale. A foot of sand, then a few inches of laminated mud with curled desiccation edges, then sand again. In such couplets, the Permian becomes personal. Even the dust speaks. The interiors of large continents produce wind-blown silt known as loess when rivers and dry lakes provide supply and winds are strong and persistent. Though the most famous Lewis blankets belong to later periods, there is growing recognition that during the Permian the interior of Pangaea raised large dust plumes. These finds settled across floodplains and in shallow seas, adding a subtle but measurable contribution to sediment budgets. Dust also fertilizes the ocean by delivering iron and phosphorus to surface waters. In a world where circulation was focused through fewer marine gateways, the balance between nutrient delivery by rivers and by dust would have mattered to planktonic life, and therefore to the entire marine food web. All of this is held within the broader frame of tectonics that never truly sleeps. Even as Pangaea enjoyed its imposing unity, the mantle currents that helped bring it together continued to evolve. The balance between the push at spreading ridges and the pull of subducting slabs does not freeze. Volcanic arcs rimmed parts of the supercontinent. Faulting and subtle stretching began to test the strength of its interior as deep currents reorganized below. The history of these first experiments in rifting will come to dominate the later Mesozoic. In the Permian, they are whispers rather than full sentences, but they are present, and they add a faint tension to the landscape. Basins subsided and filled at different rates. Some mountain belts continued to rise as the last energy of collision dissipated. Others began to relax and shed smaller and finer sediment as slopes gentled and relief softened. To walk through the Permian world in the mind is to pass from a coast gripped by seasonal rains to a mountain front lined with alluvial fans, then down a long gradient into a basin where dunes march and small rivers hide in their own sand. It is to look up at a night sky made sharply brilliant by dry air, and to imagine the watchful patience of animals that have learned to live in burrows and to feed at times when the heat relents. It is to sit in the shade of a conifer whose waxed needles barely stir in a breeze, and to hold a seed fern leaf between finger and thumb while the smell of resin and dust carries over a plain that will not see rain until the next tilt, the season. The Permian is austere and beautiful and full of invention. It is not a world unkind to life. It is a world that asks for specific answers. Those answers will decide which lineages prosper when fortunes turn. Walk into the Permian interior, and the first thing you notice is who holds the ground. The amphibi, an empire of the carboniferous swamps, has retreated to the margins where water is permanent. The plains and uplands now belong to amniotes, animals whose eggs carry their own private ponds and allow a full life cycle away from rivers and backwaters. That single innovation unlocked the vast central acreage of Pangaea. Across dune fields, along seasonally dry rivers, and on the flanks of long mountain fronts, vertebrates that conserve water and heat are the rule. This is the age when the grand experiment of land life becomes confident. Synapsids and reptiles, cousins with different trajectories, divide the landscape into hunting grounds, browsing grounds, and refuges. The record they leave is wonderfully tangible. There are bones, certainly, but there are also trackways stitched across ancient dunes, burrows spiraling into floodplain soils, coprolites packed with crushed shell or plant fibers, and bone histology that reads like a cardiogram of growth and metabolism. Early in the Permian, the most imposing animals on land are synapsids. The popular image is a predator with a tall sail and a skull crowded with slicing teeth, and there is truth in that picture. Dimetrodon stalked river margins and low plains from what is now Texas through the American Southwest, a top hunter with a deep skull, enlarged temporal openings for strong jaw muscles, and a spinous crest that likely played a role in display and in the way it managed body temperature from cool morning to hot afternoon. Close by, in time and space, the herbivore Edaphosaurus moved more deliberately through the same habitats. Its own sail bore crossbars that stiffened the structure and anchored tissue, a latticework that adds a curious beauty to the skeleton and speaks to muscular control. Beyond these celebrities stood a wide cast. Cassides such as Cotylorhynchus lumbered as huge, barrel-chested herbivores with small heads and immense bellies, bodies that suggest fermentation chambers needed to digest tough, dry vegetation. Captohinids, small reptiles with multiple rows of teeth in the jaw, worried plant matter with a rasping action, and hint at the growing importance of seed plants in the diet of land herbivores. Temnospondal amphibians like Eriops still crowded the banks of permanent water, where their broad skulls and tooth-studded palates made them efficient ambush predators. But away from the water, their hold was thin. Dry air and long droughts set terms that amphibians could rarely meet. The Middle Permian sees a changing of the guard within the synapsids as therapsids rise. The term mammal-like has been used so often that it sometimes hides the precision of what we can see in the bones. Limbs pivot a little closer to the body, which improves stride and endurance on land that asks for daily kilometers. The vertebrae and ribs arrange to frame a deeper chest. Jaws acquire a more complex joint, and teeth begin to specialize into incisors for nipping, canines for piercing, and postcanines for slicing and crushing. In some clades, the roof of the mouth starts to form a secondary palate that allows breathing while chewing. Such features are not cosmetic. They let an animal bite with accuracy, ventilate efficiently, and process food more completely. In the drier interior of Pangaea, those traits are survival tools. Therapsids diversified into an impressive array of forms. Dinocephalians were large-bodied and heavy-limbed, some herbivorous and some predatory, with skulls that thicken into bosses and arches. The bone shows signs of vascular activity and rapid growth. Animodonts included the Dicynodonts, a clade of beaked herbivores that ranged in size from burrowers to animals the size of a small cow. Their skulls carried strong adductor muscles, and the beaks could crop woody stems and fibrous fronds with efficiency. Crowds of small Dicynodonts built interconnected burrow systems in the late Permian Karoo of South Africa. Whole pairs of curled skeletons lie preserved within spiral burrows that dip into ancient floodplain muds. These are living arrangements for a climate that punishes the careless. Burrows moderate heat and cold, conserve humidity, and offer safe nurseries. At the sharp end of the food web were Gorgonopsians and their relatives, sleek predators with long canine teeth and flexible necks. The Russian giant Inostransevia, with a skull the size of a lion and saber-like canines, is a reminder that the top carnivores of the late Permian were therapsids rather than reptiles. Therocephalians and early cynodonts add further variety, some with delicate teeth that suggest insectivory, others with robust jaws that hint at bone cracking. Within the cynodonts, we catch the first clear moves toward the architecture of mammals. The lower jaw is composed of fewer bones with a large dentary. The teeth are deeply differentiated, and there are hints of a soft tissue muzzle with sensory vibrissae inferred from foramina and grooves. Those inferences are strongest in early Triassic forms, but their roots reach into the late Permian. Bone tissues support the story of elevated performance. Under a microscope, the long bones of many therapsids show fibrolamellar bone, a tissue built quickly and efficiently, full of blood vessels and woven fibers, a scaffold for rapid growth. In contrast, slow-growing reptiles often build lamellar bone with fewer vessels and a more orderly fabric. Growth rings reveal pauses and spurts. In the Permian interior, where seasons are sharp and food pulses with the monsoon, that pattern makes ecological sense. There are lines that mark seasonal slowdowns and zones where growth resumes with vigor when rivers run and plants flush green. Skeletal pneumaticity is absent, and true turbinate bones are not preserved, so a full picture of respiration awaits softer evidence than bone can give. Still, snout grooves in some forms and deep nasal cavities in others hint at soft tissue that warmed and moistened inhaled air. The ensemble of traits suggests that at least some therapsids had metabolisms higher than those of contemporaneous reptiles. Perhaps not yet like a modern mammal, but well beyond the strictly sluggish. Life in the interior deserts encouraged more than physiology. It shaped behavior. Burrowing is one expression we can see, and it is not limited to small herbivores. Predators also use dens. In the Karoo and in Russia, there are bones of juveniles with adults in what look like shared shelters, a scene that implies parental care. Parental care is not a mammal invention. It evolves wherever young are vulnerable and the return on investment is high. Another behavioral adjustment that the rocks and teeth betray is diet flexibility. An animal that can eat seeds, young shoots, and tough evergreen leaves from conifers has a better chance of spanning a long dry season than one that depends on seasonal soft vegetation. Tooth microear and the proportions of grinding surfaces in postcanine teeth tell us which species took that flexible path. The dicynodont beak and the postcanine wear in some cynodonts combine to paint a portrait of animals that processed food thoroughly to extract every calorie and every drop of water. The Permian also produced some of the strangest herbivores to walk the earth. Paraeosaurs were heavy, short-faced, broad-bodied reptiles armored with pebbly osteoderms. Their skulls are decorated with bosses and ridges, ornament that may have signaled maturity and helped in social contests. They were common across Pangaea in the Middle and Late Permian, often in the same basins that hosted therapsids. Their teeth bore leaf-shaped crowns with multiple cusps designed to shear and mash. In some localities, their bones are so abundant that their death and decay left a measurable chemical signal in the sediments. The rise of herbivory on land was only a few tens of millions of years old, and the variety of solutions on display during the Permian is astonishing. There are barrel chests that house pouches of fermenting microbes, dental batteries that grind like mills, and cropping beaks that strip tough stems. Each of these solutions leaves a signature in form and in microwear, and each can be matched to the plants that span the basin floor. Predation provokes innovation. Gorgonopsians had skulls built to deliver a decisive bite. The jaw muscles attached to crest and scar are large, the canine teeth are long and laterally compressed, and the neck vertebrae are stiff enough to anchor a strike. Trackways of potential prey show tight clusters of footprints, as if animals moved in small groups for protection. Hiding in burrows and using the shade of scattered trees are obvious simple defenses. More subtle ones are harder to see. There are hints in bone chemistry that some herbivores shifted their range seasonally to follow green belts along rivers. A migration in miniature that keeps distance between themselves and the dens of large predators. There is also the ancient problem of heat. A hunter that chases in full sun must avoid overheating. That may be one reason why many predators hunted at dawn and dusk. Nighttime hunting requires senses tuned to dim light and to sound and scent. The skulls of some therapsids carry enlarged canals that transmit nerves to the face, a feature that suggests a sensitive muzzle and perhaps whiskers that could read the environment in darkness. The Permian night belongs to such animals. While the land was discovering new ways to be vertebrate, the seas around Pangaea were discovering their own set of winners and losers. Reef building was still strong along warm margins, but the architects had changed from the coral-dominated communities of the earlier Paleozoic toward sponges and calcareous algae that tolerated the chemistry of Permian seas. Among invertebrates, fusulinid foraminifera grew to sizes and abundances that are hard to imagine for a modern unicellular organism. Their rice-shaped shells pile into limestones that stretch for kilometers. Producted brachiopods, with broad concave shells, carpeted the sea floor in beds. Nautiloids and ammonoids roamed as active predators, their shells coiled with mathematical precision and divided into chambers by septa, whose edges grew ever more elaborate. The flourishes in septal design increase shell strength and may have had physiological implications for buoyancy control. Trilobites, the icons of a much earlier world, persisted in only a few lineages and were shadows of their former diversity. They would not survive the boundary that ends the Permian. Among fishes, the story arcs toward modernity. Actinopterygian bony fishes expanded in variety and refined jaw mechanics that allowed quick suction feeding, while coelacanths and lungfish, descendants of ancient lobe-finned ancestry, explored both open waters and nearshore habitats. Sharks with robust spines and sturdy fins patrolled near reefs, and in fresh waters of the interior, xenocanth sharks with eel-like bodies and a distinctive fin spine swam in rivers and lakes that sometimes dried to brine. Even insects tell a Permian tale. The atmosphere probably had a lower oxygen concentration than during the Carboniferous, and that change pinched the maximum size reachable by air-breathing arthropods. The roster of insect groups shifted. Paleodictyopterans, an early experiment in flight, declined and vanished. Groups with the complete metamorphosis that defines modern beetles, flies, and wasps took early steps toward later success. The earliest confident beetle fossils are Permian. Their hardened forewings and compact bodies are well suited for life among litter and bark in a world where fire and drought are common. Wing venation charts the changing balance between agility and power in the air, and mouthparts record a buffet that tilted toward seeds and dry leaves rather than tender submerged plants. The proliferation of conifers, cycads, and seed ferns gave insects a new catalogue of food and shelters, and the insects answered with new forms and habits. If you pull back and take the long view, the Permian on land is a rehearsal for the Mesozoic. Many of the features that will later characterize the most successful Triassic and Jurassic animals are present at the end of the Permian in recognizably early form. Efficient gaits, rapid growth, complex dentitions, social behaviors anchored by burrows and parental care, and ecologies that fill the spectrum from tiny nocturnal insectivores to large daytime grazers and apex predators are already in place. The land food webs are deeper and more resilient than before because there are more ways to be a plant eater and a hunter in an arid and seasonal world. The oceans are rich but stressed in places, with reefs that depend on clear, warm water and basins that sometimes flirt with low oxygen. The stage is set for a trial. It will arrive with the most severe extinction event known, a crisis that will prune the tree of life to its thickest branches and reset many of the experiments just described. But before that reckoning, the Permian world deserves to be seen for what it is. It is not merely a prologue, it is a peak of its own. Evidence for all of this comes to us from rocks that are accessible with boots and a hammer, and also from laboratories where thin slices of bone are polished to translucence. It comes from the Karoo Basin, where an entire living world is layered in mud and sand, its changes paced by shifting climate and sea level. It comes from the Permian Basin, where fossil reefs stand like walls and teach us about chemistry and community in ancient seas. It comes from red sandstones on 3 continents, where wind-built dunes and reptiles climbed them. It comes from the smallest of details, such as a set of pits along a snout that suggest a sensitive face, or the angling of a limb joint that hints at an efficient stride. Science is the practice of connecting such details with care and argument, and testing those arguments with new finds and better tools. The Permian deserves that effort because it is the last act before a curtain that falls with unusual force. The phrase "conquerors of the land" is not idle. The animals that thrived on Pangaea did so by mastering the physics of heat and water. They sealed their skin, regulated their internal temperature with behavior and physiology, conserved moisture in renal systems that produced dry waste, and, when possible, retreated into the ground itself. They timed their reproduction to take advantage of pulses of food, and at least some protected their young to increase the odds that the next generation would inherit the ground. They edited the old amphibian blueprint for limbs and lungs into something more robust and efficient. In doing so, they created lineages that would carry through the worst of times and then expand again. The next chapter will hold hard news. For now, it is enough to see the Permian as a success, a summit on which many life stories were already fully formed. Long before the curtain fell on the Permian world, the rocks began to whisper that something was wrong. In shallow tropical shelves that once carried bright reefs, scaffolds of sponge and algae give way to dull muds. Thick limestones that spoke of clear, warm water thin and vanish, replaced by dark shales laid down where oxygen was scarce. Far inland, coal formation falters in equatorial belts and then stops altogether for a long span that geologists call the coal gap. Rivers still ran, but swamp forests that once locked carbon into peat withdrew or collapsed, a sign that the climate machine had begun to favor heat and dryness over steady moisture. Chemistry records the warning in a more clinical hand. Carbonate rocks and organic matter carry a strong fall in the ratio of heavy to light carbon, the famous negative carbon isotope excursion that marks a rapid injection of light carbon into the atmosphere and ocean. Such a signal points to giant sources, either massive volcanic gases or methane released from seafloor hydrates and soils. At the same time, oxygen isotopes in conodont tooth enamel indicate a sharp rise in seawater temperature. Reconstructions suggest warming on the order of many degrees across the globe, a heat wave on geologic terms that arrived faster than ecosystems could track. The likely trigger stands on the map of Siberia. There, a flood basalt province the size of a continent erupted around the Permian-Triassic boundary. Through thousands of fissures, magma rose to the surface and spread in stacked sheets that are today called the Siberian Traps. The volumes are scarcely believable. Lava flowed across plains and into basins in repeated pulses. More damaging than the heat of lava was the gas. Carbon dioxide and sulfur species vented in colossal amounts. The magma also invaded thick sediments rich in organics and evaporites. As those sediments were baked, they released more carbon, methane, and halogens. Around the world, layers that bracket the boundary show spikes in mercury and nickel, chemical fingerprints that match the types of deposits in Siberia and serve as a global flare announcing faraway eruptions. The oceans felt the insult first and hardest. Warm water holds less oxygen. As temperatures rose, deep basins slid toward anoxia. In many places, the water column not only lost oxygen but became sulfidic, a condition called euxinia. Tiny pyrite spheres settle by the millions in the black shales of this time, and molecular fossils of green sulfur bacteria appear, organisms that can only thrive where light and hydrogen sulfide meet. That geometry exists in a shallow chemocline. It implies that stink and poison climbed high in the water column and spread across broad shelves. Reef builders could not endure. Many calcareous sponges and corals vanish. Shelled swimmers that once crowded the seas shrink in diversity. The entire architecture of marine food webs sagged as the base of the pyramid failed. Life on land faced its own series of blows. Heat and aridity intensified across interiors. Forests that were already tuned to drought reached a threshold and broke. Glossopteris-dominated woodlands in Gondwana disappear from the record. Pollen and spores show turnover in plant communities on a continental scale. Charcoal layers tell of frequent wildfires, fueled by seasonal drought and by litter from dying stands. Some sections record a short-lived spike in fungal remains, once touted as a fungal bloom that consumed dead wood on a global scale. The signal now seems more complex and patchy, but the broader message is secure. Decomposition surged across huge landscapes. Soils stripped from slopes and poured into basins. Rivers responded with unstable channels and with floods that carried coarse loads. Invertebrate burrows thin out in floodplain strata, and vertebrate trackways become rare. A quiet testimony to reduced abundance. The rock clock reveals that change did not land in a single blow. Through the late Permian, extinction arrived in steps. Some groups fade early, others hold on until the final pulse. The main crash falls very near the formal boundary. High-precision uranium lead dates from ash layers in China and South Africa place the most rapid losses within a narrow window that may be measured in tens of thousands of years rather than millions. To a biosphere, that is a blink. The Maishan section in Zhejiang, a thin cliff of stacked limestones, marls, and volcanic ash, has become the reference wall for this story. There, a sharp fall in carbon isotopes, a turnover in conodont faunas, and the loss of many shelly groups coincide within a bed you could jump across. Other stressors likely joined the coup. Acid rain from sulfur-rich emissions would have gnawed at soils and fresh waters. If halogen gases released from baked evaporites reached the stratosphere, the chemistry of ozone could have been disturbed, letting more ultraviolet light strike the surface and injure plant tissues and plankton. Methane may have bubbled from heated shelves and permafrost, further lowering the carbon isotope ratio and amplifying warming with a strong greenhouse pulse. The sum need not be one mechanism. Earth systems fail in cascades. Volcanism starts the fall, climate tips, oceans lose breath, fires rage, soils wash away, and food webs unravel. In the final 100,000 years of the Permian, the warnings become a siren. Reef belts stop, coal formation nearly ceases, anoxia spreads across basins on every mapped margin. On land, vertebrate communities thin to a few hardy forms in the record. And in some places, therapsids vanish from entire basins, with only isolated survivors trickling into the earliest Triassic. The signal is clean and global. It appears in the Karoo of South Africa, in the basins of the Urals, in the stacked carbonates of South China, in the shelf successions of Western North America, and in the high-latitude rocks of Australia and Antarctica. The planet had moved into a new and dangerous state, and the Permian world was not built to hold it. At the boundary itself, the story stops being a set of warnings and becomes a collapse. In marine rocks, the familiar cast of the Paleozoic vanishes in a geologic instant. Rugose corals and tabulate corals, architects of earlier reefs, do not cross the line. Many families of brachiopods disappear together with most trilobites, and ammonoids shrink to a few hardy lineages before their brief rebound. In shallow seas, black shales thicken and spread, loaded with pyrite framboids that form where oxygen is scarce and where hydrogen sulfide seeps into sunlit water. Biomarker molecules from green sulfur bacteria appear in sections that were once bright carbonate shelves, proof that sulfidic waters had climbed into the photic zone. The physical mood of the ocean changed as well. Warmer surface waters held less oxygen and mixed poorly with the depths. In this stratified sea, large regions entered a state of near-permanent breathlessness. The scale of loss is difficult to grasp. By many counts, more than 4 of every 5 marine species died. On land, roughly 7 in 10 species of vertebrates vanished. Plants in many regions suffered sweeping turnovers. Insects, usually resilient through deep time, record the only major extinction known for their class. The catastrophe was global, and it unfolded quickly. At Meishan in China, a single thin set of beds captures a sharp plunge in the ratio of heavy to light carbon, together with the disappearance of a long list of fossil groups. High-precision uranium lead dates from volcanic ash layers in multiple basins fix the most intense interval of extinction to a window that is far shorter than 1 million years. For complex communities that had been stable for tens of millions of years, that was not enough time to adapt. The Siberian traps eruptions stand behind the curtain with a relentless patience that geology can deliver. Over many pulses, magma rose through a crust rich in organic matter and salts, baked it, and released volatile gases, while lava spread across a continent-sized province. Carbon dioxide poured into the air and warmed the planet. Sulfur species injected into the stratosphere would have produced acid rain and short-lived cooling, followed by longer warming as greenhouse gases accumulated. Halogens released from heated evaporites may have damaged the ozone layer, allowing more ultraviolet radiation to reach the surface. The geologic record preserves a suite of corroborating signals. Mercury spikes sit in boundary beds on several continents. Nickel-rich ash and aerosols are captured downwind in sediments. Large negative excursions in carbon isotopes point to fast injections of light carbon that can be explained by volcanic sources and by destabilized methane in shallow seas and permafrost. Acidification of seawater added a second insult. As carbon dioxide dissolved into the ocean, it lowered pH and made carbonate ions less available for shells and skeletons. Evidence for this shift comes from boron isotopes that track seawater acidity and from calcium isotopes that register changes in the global balance of carbonate precipitation and dissolution. In the rock record, the carbonate factory fails. Bright platform limestones give way to thin microbial crusts and to mud bound by bacterial mats. These microbialites flourish as classic disaster forms because the grazers that once kept such mats in check were decimated. Sediment surfaces preserve wrinkle structures and gas escape textures that are common when microbial blankets seal the sea floor. Even surviving shelly animals show the Lilliput effect, a tendency toward much smaller adult size in the aftermath of ecological collapse, likely a response to heat stress, low oxygen, and food scarcity. The story on land is equally stark. In Gondwana, the glossopterid forests that had dominated temperate belts fade and vanish. Spore and pollen assemblages flip toward forms that prefer heat and dryness. In many basins, there is a coal gap that spans several million years across the boundary, a silence that tells us peat-forming wetlands nearly disappeared. Sedimentology speaks of naked slopes and unstable rivers. Channels that once meandered across vegetated plains cut deeply and shifted without restraint, carrying coarse loads into new fans and filling lakes with pulses of sand and silt. Charcoal beds are common and suggest frequent fires during seasonal droughts. In some sections, researchers have reported malformed spores with thickened walls and damaged cell divisions, a pattern consistent with increased ultraviolet stress during a time when the ozone shield may have been compromised, although the signal varies by region and is still debated. Survival was selective. Traits mattered. In the sea, organisms that relied on high oxygen levels, that lived on well-aerated shelves, or that used energetically expensive forms of calcification were hit hardest. Taxa that tolerated low oxygen, that used flexible diets, or that lived in deeper and cooler waters sometimes held on. On land, animals that could burrow, that bred quickly, and that managed water well had an advantage. The early Triassic vertebrate record across southern Pangaea is famously dominated by Lystrosaurus, a medium-sized dicynodont with a beak for cropping tough vegetation and a body plan that suggests endurance. Its fossils appear from South Africa to India to Antarctica, a distribution that tells of both broad tolerance and a landscape flushed of many competitors. Other survivors included small cynodonts and therocephalians that used burrows and parental care, procolophonids with sturdy skulls and generalized diets, and temnospondyle amphibians that lived where water persisted. The living communities were simpler. Food webs were shorter and built on opportunism. Recovery was not immediate. In the oceans, conditions oscillated between partial improvement and renewed stress through much of the early Triassic. The carbon cycle swung wildly as weathering intensified on land and as volcanic outgassing continued. Repeated episodes of anoxia returned to continental shelves and delayed the re-establishment of complex reefs and stable faunas. The Induan and early Olenekian stages are filled with microbialites and with small opportunistic shelly faunas. Only by the Middle Triassic do fully developed reef systems reappear, now built by scleractinian corals rather than by the Paleozoic groups that were lost. Ammonoids radiated rapidly, filling open niches with spectacular ornament and variety. Bony fishes diversified and refined jaw mechanics that would characterize modern clades. Conodonts also survived and changed, and the first appearance of Hindeodus parvus defines the very base of the Triassic in the global timescale. On land, the first few million years after the boundary were harsh. Climate models and isotopic proxies suggest tropics that were extremely hot, with sea surface temperatures in some regions exceeding levels that challenge modern marine life, and with broad belts of aridity across the interior of Pangaea. Forests were slow to return. Many landscapes were open, dominated by scrub and by drought-resistant plants. The vertebrate faunas of the earliest Triassic have a signature of small body size and rapid growth. Lystrosaurus remains common well into the Olenekian, before more diverse faunas arrive. Through time, archosaur relatives begin to appear alongside the surviving synapsids, and by the late Triassic, they will hold many of the top predator and large herbivore roles on land. The earliest true conifers and ginkgo relatives expand, and seed-bearing plants reshape the plant-insect dialogue, setting the stage for new pollination strategies that will come to fruition later with flowering plants. The timescale of full ecological recovery is measured in millions of years, and it varies by environment. Some marine communities regain diversity within about 4 to 8 million years, while complex reef ecosystems took longer. On land, the return of extensive forests lagged behind, but by the Middle Triassic river systems, once again meandered through well-vegetated plains and flood basins, supported complex food webs that included early dinosaurs, large amphibians, crocodile-line archosaurs, and a new diversity of synapsids. The planet did not return to the Permian. It wrote a different chapter with new engineers of energy and matter. Coral reefs were built by different corals. The top hunters on land belonged to different families. The survivors had inherited a warmer and often more seasonal world, and they evolved into it. There is a lesson in this arc from warning to collapse to halting recovery. Earth systems are connected. A change in volcanic flux altered climate and ocean chemistry, and those in turn altered the structure of ecosystems, which then fed back into the carbon cycle. The slow rebound shows that once the fabric is torn, it takes time for interactions to weave again. The end Permian crisis did not simply prune the tree of life. It rewrote the rules about who could thrive under a new sky. Out of that rewrite came the Triassic world that will raise the archosaurs and eventually the dinosaurs, and a marine realm that will rebuild its scaffolds with new architects. The Great Dying was an end, and it was also a beginning. From the silence that followed the Great Dying, the world began to speak again, softly at first. The early Triassic opens on landscapes that are stripped and raw. Hillsides are scarred by floods, river channels wander without restraint, and broad floodplains shimmer with heat. In many basins, the first beds above the boundary are microbialites, knobbly limestones built by mats of bacteria that spread where grazers and reef builders had vanished. The ocean is warm and often breathless. On land, forests are scarce. Yet even in this spare scene there are pioneers, organisms that move quickly into empty space and begin the slow work of rebuilding a biosphere. The map is still the map of Pangaea. A single supercontinent girdles much of the globe and is surrounded by the world ocean of Panthalassa. Along its eastern indent lies the Tethys, a long tropical seaway that will grow in importance as the Triassic unfolds. Geography still dictates climate. The interior of the continent remains arid and seasonal, but the contrast between coast and interior is sharper now because vegetation no longer softens the climate. With shallow-rooted plants gone, soils are loose and mobile. Rivers respond with braided channels that carry coarse loads. When the monsoon breathes in summer, torrential rains scour slopes and fill ephemeral lakes. When the breath reverses, dust rises in vales and dunes advance. Mud cracks and raindrop imprints are common on bedding plains. Small records of heat and sudden rain written a few minutes apart. The oceans show a similar rhythm of stress and halting recovery. The earliest Triassic stages bear witness to anoxia that continues to spread across shelf seas. Black shales, and the chemistry of sulfur record intervals when hydrogen sulfide reached into sunlit water. Reef ecosystems are gone. In their place, stromatolites and thrombolites flourish across large areas, a reminder that microbial communities thrive where metazoan grazers are rare. Through the Induan and into the Olenekian, the carbon cycle swings widely, with isotopic excursions that signal climatic volatility. The Smithian warming event pushes tropical sea surface temperatures to extremes and is followed by a cooling step in the Spathian, an oscillation that delays recovery and repeats local pulses of extinction. Only later in the Triassic do stable carbonate platforms return, and when they do, the principal builders are the new scleractinian corals rather than the Paleozoic architects that had vanished. On land, the signature of collapse is clearest in plants. There is a prolonged coal gap in many equatorial and mid-latitude basins. Peat-forming wetlands either vanish or contract to refuges. Pollen and spore assemblages show a turnover toward drought-tolerant forms. Early Triassic floras are often dominated by fast-growing pioneers, such as ferns and sphenopsids, that recolonize scoured ground after floods and fires. Through time, conifers and seed ferns spread again along river corridors and lake margins. In Gondwana, glossopterid forests do not return, and their absence is one of the most visible botanical losses of the event. Where wood is preserved, growth rings are narrow and irregular, an anatomical memory of short seasons of abundance punctuated by stress. Among vertebrates, a single name becomes a watchword for survival. Lystrosaurus, a medium-sized dicynodont with a beak and a barrel chest, proliferates across southern Pangaea in the earliest Triassic. Its fossils appear in South Africa's Karoo, in the Indian subcontinent, and in the transantarctic basins, a distribution that was possible only when those lands were united. Anatomy tells us why it did well. A simple but powerful jaw apparatus allowed efficient cropping of tough vegetation. A robust body with strong forelimbs suggests digging and a capacity for endurance. The bone tissue shows relatively rapid growth, with pauses that track seasonal hardship. Put together, this is an animal built for drought, heat, and resource pulses, precisely the conditions that ruled the early Triassic interior. Lystrosaurus was not alone. Therocephalians and early cynodonts, small synapsids with differentiated teeth and improved ventilation, persisted in burrow-rich floodplains. Procolophonids, compact reptiles with sturdy skulls and generalist diets, became common residents of disturbed habitats. Large temnospondyle amphibians survived wherever water was reliable and sometimes grew to impressive sizes in lakes and sluggish rivers. Their presence signals that permanent aquatic refuges remained even in an otherwise harsh climate. Trackways from early Triassic beds show low diversity but high abundance for a few hardy forms. And burrowcasts record a landscape where many animals escaped heat and predators by living underground much of the day. Changing rivers and soils carry their own data. Sediment packages in South Africa, Russia, and China record flashy discharge and repeated channel avulsions through the earliest Triassic, as if the plumbing of the continent had been shaken. Thick sets of cross-bedded sands point to strong seasonal winds. Calcrete horizons in red beds show that evaporation remained intense. In several basins, thinly laminated lake deposits contain varves, whose bundles thicken and thin with orbital cycles, revealing that the monsoon itself waxed and waned over thousand-year scales. Even in crisis, Earth's climate machine kept its celestial timing, and that regularity offers a metronome against which we can pace the return of life. By the Middle Triassic, the picture brightens. Stable river belts return, and meanders reappear where banks can once again hold against the current. Forests of conifers, cycads, and ginkgo relatives spread along floodplains and low uplands, and leaf litter once more blankets the ground. Insects diversify and refine modern guilds. The seas see the first complex reefs re-established in favorable settings. Ammonoids radiate into a spectacular array of coiling forms and rise quickly through the food web. Bony fishes expand in diversity and jaw mechanics that allow fast suction feeding become widespread. The earliest marine reptiles appear in the record, including long-bodied ichthyopterygians, such as Chauhusaurus and Utatsusaurus, that hunt in nearshore waters, and the first nothosaur-line swimmers begin to explore the Tethyan margins. Their arrival marks a major ecological shift in coastal seas, where reptiles will become important predators for the rest of the Mesozoic. Even as communities recover, the architecture of the Triassic world is new. Microbial mats remain common on some shelves. Reef builders are different. Plant lineages that prosper are adapted to seasonal drought. On land, the dominant large herbivores and predators will soon transition from synapsid survivors to archosaurs and their close relatives. The first steps of that transition are already visible in the late Olinekian and Anisian, when early archosauriforms begin to share floodplains with the descendants of Permian lineages. The stage that the Great Dying cleared is now populated by actors that favor speed, efficient gaits, and water-saving physiology. The supercontinent has not moved far, but the rules of success on its surface have changed. Recovery after the greatest crisis in the Phanerozoic took time, but it was not a simple return to what was lost. It was a reassembly and a reimagining. Rivers found stable courses again because roots once more knit banks together. Forests returned because drought-tolerant plants discovered corridors where groundwater and soil moisture persisted across seasons. Reef ecosystems were rebuilt by new corals and by new partnerships with symbiotic algae. The nascent marine reptiles seized a niche opened by the collapse of earlier predatory guilds. The simple faunas of the earliest Triassic gave way to layered food webs in which energy and matter moved through many hands before reaching the top. The phrase Triassic rebirth is not only rhetorical, it describes a genuine increase in complexity and productivity after a near-mortal wound. The evidence lies in the rocks, in the chemistry of carbon and sulfur, in the growth rings of conifer wood, in the microscopic tissue of synapsid bone, and in the quiet pairing of laminae that counts years in lake mud. From this careful record, we learn that life is resilient, but that recovery can be slow and path-dependent. The world that emerges is suited to a warmer and more seasonal planet. It is the world that will soon support the rise of the archosaurs and the first true dinosaurs, and that will send lineages back into the seas with bodies shaped for water. The relief after the Great Dying did not immediately produce a gentle world. It produced a competitive one, and in that arena, a new coalition of reptiles rose to prominence. These were the archosaurs, the ruling reptiles in the strict sense, named for skull openings and ankle designs that speak to power and efficiency. The diagnostic window is an extra hole in front of the eye, the antorbital fenestra, and a second opening in the jaw, together with a strengthened ankle that could channel force cleanly through the limb. The package matters because it supported a more upright posture, faster strides, and better breathing during motion. In a hot and seasonal Triassic, when many landscapes still flipped from flood to drought, those traits were tickets to success. At first, the archosauriform scene reads like an experimental workshop. Early forms such as proterosuchids and erythrosuchids walked with sprawling or partly upright limbs and carried deep skulls with large jaw muscles. Soon, the archosaurs proper split into two grand lines that would shape the rest of the Mesozoic. One branch would lead to crocodiles and their kin. The other branch would lead to pterosaurs and dinosaurs. The split is marked in the ankle. In the crocodile line, the joint allows a twist between the astragalus and calcaneum, so the foot can rotate while keeping purchase on uneven ground. In the bird line, the ankle behaves more like a simple hinge, a design that favors an elegant, upright gait and long, efficient steps. It is a small engineering difference with large ecological consequences. On the crocodile line, called the pseudosutians, diversity exploded. Some members became the bulldozers of floodplains. Etosaurs were heavy-bodied herbivores with armor plates in neat rows over the back and sides, shovel-like snouts for rooting, and small leaf-shaped teeth for cropping. Their footprints pace the margins of Triassic rivers from Europe to the American Southwest, and their carapace patterns are as distinctive as fingerprints. Other members return to the water as ambush hunters. Phytosaurs look like crocodiles from a distance but place their nostrils near the eyes rather than at the tip of the snout. They patrolled oxbows and coastal lagoons and launched upward through the surface at fish and unwary land animals that came to drink. The top carnivores on land in many late Triassic communities were Rauisuchians and their close relatives, immense predators with pillar-like hip joints that set the hind limbs straight beneath the body. Their skulls were deep and armed with curved teeth set to shear flesh. Trackways and bone beds show that such animals occupied the apex positions once held by Permian Gorgonopsians and large dinocephalians, a handover forced by extinction and sealed by new anatomy. At the same time, the bird line, the Avemetatasalians, pursued a different solution. The ankle hinge, the elongated lower leg, and a tendency toward light skeletons created a style of movement that conserved energy over long distances and made speed more economical. That design found its first dramatic expression in the air. Pterosaurs appear in the late Triassic, with wings built from a skin membrane stretched along an elongated fourth finger, a shoulder anchored by strong muscles, and bodies that show evidence for a coat of fine fibers called pycnofibers that lightly insulated and smoothed airflow. Their early representatives, among them species from northern Italy and Central Europe, already show grasping feet and a full flight apparatus. They took fish on the wing over lagoons, hunted insects above coastal plains, and perched on cliffs that ringed the Tethys. They are the first vertebrates to achieve powered flight, and their appearance signals that Triassic ecosystems could now partition the sky as well as land and sea. On the ground, the story slowly bends toward dinosaurs, though at first the stage is crowded with their close cousins. Lagopetids and Silsaurids occupy light-footed insectivore and herbivore niches, and carry many of the hallmarks of the bird line without yet being true dinosaurs. In the southern tropics of Pangaea, especially in the basins of what is now Argentina and Brazil, the record sharpens. The Santa Maria and Ishigualasto formations preserve floodplains that saw frequent ash falls and rapid burial, an ideal setting for copying communities into stone. There, small early dinosaurs took shape among a cast of pseudosutian predators, large amphibians, and surviving synapsids. Eoraptor was a nimble omnivore with a lightly built skull and grasping hands. Herrerasaurus and Staurikosaurus were fast bipedal predators with long tails for balance and hind limbs built for a ground-covering stride. In North America, Coelophysis filled the role of a slender pack-hunting carnivore in the late Triassic Chinle Formation, its mass graves pointing to drought or flood catastrophe on floodplains that could turn cruel without warning. The geographic spread of these forms, together with older footprints of dinosauromorphs that predate many body fossils, suggests a slow but steady radiation out of southern refugia into the wider Pangaean landscape. Why this rise, and why in the Triassic climate? Part of the answer lies in physiology and airflow. Archosaurs likely possessed lungs that moved air in a single direction through rigid tubes, with balloon-like air sacs acting as bellows. Modern birds use such a system, and modern crocodilians also show unidirectional airflow, which implies the pattern may be ancient within the group. Such lungs extract oxygen efficiently and work well during sustained activity, which matters in heat where panting can waste water and where a runner must keep breathing while sprinting. The upright posture of many archosaurs lifted the trunk off the ground and freed the chest from the mechanical constraints seen in animals that must push their bodies from side to side as they walk. The resulting stride is economical. In bone, the story is written as gracile limb shafts with powerful muscle scars, as long metatarsals that lengthen the leg lever, and as fused or simplified ankle elements that transmit force cleanly. Climate variability likely offered a second advantage. The Triassic was a world of seasonal extremes in many regions. Fast growth to reproductive age is a hedge against bad years, and bone histology of early dinosaurs and of many pseudosutians records rapid growth with growth rings that track seasonal slowdowns. Eggs with leathery shells are relatively cheap to make, and a strategy that produces many eggs and spreads risk across nests and seasons is sensible when drought or flood can erase a cohort. Trackways sometimes show parallel paths of multiple individuals of similar size, a hint that at least some archosaurs moved in groups, which can improve foraging and defense in open floodplain habitats. The plant world these animals inhabited was changing as well. Conifers, cycads, ginkgo relatives, and seed ferns built mosaics of woodland and open savanna on well-drained soils, while wetter belts along rivers carried taller forests. The Carnian interval brought a global pulse of humidity known as the Carnian pluvial event. For a time, many basins record increased rainfall, lake expansions, and a shuffle in plant communities. Some researchers link this humid pulse to volcanic activity on what is now the Pacific margin of North America, which would have added greenhouse gases to the atmosphere and energized the hydrologic cycle. Whatever its cause, the wetter episode may have opened corridors and expanded food resources that helped dinosaurs spread. Afterward, climates in many regions returned to strongly seasonal patterns. Predator-prey dynamics illustrate how the archosaur world functioned. On floodplains of the Chinle, armor-plated etosaurs browsed low vegetation, while nimble dinosaurs and silesaurids nipped seeds and insects. Phytosaurs waited in cutbanks and snatched animals at water. Large Rauisuchians patrolled the open ground, and their trackways crossed those of herbivores like punctuation marks on a page. The system was complex, but it still lacked some of the later Jurassic specializations. Sauropodomorphs were present, but small to medium in size. True stegosaurs and ankylosaurs would come later. The skies held pterosaurs, but birds had not yet taken wing. The simplicity and plasticity of these communities made them robust to short-term stress, but vulnerable to the larger tectonic and volcanic pulses that were gathering at the end of the Triassic. Even as archosaurs consolidated their roles, geology enforced change. Pangaea began to loosen along future Atlantic and Tethyan margins. Rifts opened as long linear valleys that subsided and filled with lake sediments. The presence of permanent and deep lakes along some rifts created belts of humidity that served as biological highways. Fine laminated lake shales in these basins preserve insects, fish, and occasional early pterosaurs in exquisite detail. The chemistry of these lakes records orbital pacing of monsoons and shows that the climatic engine of Pangaea now had more moving parts. Variation in rainfall across rifts and uplands produced patchworks of habitat that favored animals with good dispersal and flexible diets. Archosaurs fit both requirements. By the late Triassic, the ruling reptiles had become the architects of most large land communities. The crocodile line supplied the top carnivores and heavy herbivores in many places. The bird line supplied small, fast predators, nimble omnivores, the first serious herbivorous bipedal forms among sauropodomorphs, and the first masters of the air. The stage was set for a decisive reshuffle at the close of the Triassic, when a new volcanic episode would thin the ranks of the crocodile line on land and hand the big game to dinosaurs. That outcome belongs to the next acts. The essential point here is that the spread of archosaurs was not an accident. It was a coordinated suite of anatomy, physiology, and behavior played on a board of shifting climate and geography, a board drawn by the lingering outline of Pangaea. The rise of the dinosaurs begins in the long shadow of crisis. Near 201 million years ago, as the Triassic closed, the Earth shuddered through a new volcanic awakening. Great curtains of lava flooded rift valleys along what would become the shores of the Atlantic. Geologists call this province the Central Atlantic Magmatic Province. The gases it bled into the air warmed the climate, disturbed rainfall, and threw ocean chemistry off balance. Many of the dominant land predators of the time, members of the crocodile line, disappeared along with giant amphibians and a suite of marine creatures. What followed was not a quiet scene of empty ground. It was a landscape of open opportunity. The archosaurs that survived included light-footed dinosauromorphs and early dinosaurs already tuned for speed, endurance, and efficient breathing. In the early Jurassic, these survivors expanded, diversified, and claimed the roles that would define the Mesozoic. The map remained the map of Pangaea, though new rifts scored its margins and collected deep lakes. In those rifts, such as the Newark basins of eastern North America, thin annual layers of lake mud stack by the tens of thousands. Their paired laminae record wet and dry seasons. Their bundles thicken and thin with celestial rhythms as Earth's orbit slowly changes. Underfoot, the floodplains still felt seasonal heat and sudden rain. The interior of the supercontinent remained arid and strongly seasonal, but along the rifts, humidity rose and shorelines offered belts of green that functioned as highways for dispersal. Dinosaur footprints stride through this record, with a confidence that body fossils alone cannot convey. Slender three-toed tracks called grallata and larger eubrontes cross bedding plains from Nova Scotia to Connecticut, and comparable ichnites occur in Morocco and Europe, testimony that fast bipedal carnivores patrolled coasts and river margins on both sides of the young rift system when the Atlantic was only an idea. By the dawn of the Jurassic, the dinosaur family tree already had its principal branches. Theropods were the carnivores, two-legged hunters with grasping hands and skulls braced for force. Sauropodomorphs were long-necked plant-eaters that began as medium-bodied bipeds and soon grew into true giants. Ornithischians were diverse herbivores with a backward-pointing pubis and a talent for chewing. Early Jurassic theropods announced themselves on several continents. Dilophosaurus ranged across desert rivers in what is now Arizona and carried a pair of thin crests on its skull that likely signaled maturity and social rank. Cryolophosaurus hunted on the uplands of what is now Antarctica, proof that dinosaurs reached high southern latitudes during warm Jurassic climates. Sinosaurus and other early forms roamed along the Tethyan margin of China. Their bones tell the same story: hollow limb shafts, interlocking ankle elements, and strong muscle scars built a stride that could cover ground without waste. Their lungs likely moved air in one direction through rigid tubes, while balloon-like sacs acted as bellows. That airflow pattern, shared with modern birds and inferred in living crocodilians, extracts oxygen efficiently and works well during sustained motion. Sauropodomorphs bridged the boundary from the Triassic into the Jurassic and then transformed. In the late Triassic, plateosaurids like Plateosaurus were tall herbivores with long necks and strong hind limbs. By the early Jurassic, true sauropods stepped onto the stage. Volcanodon in Zimbabwe and Tazutosaurus in Morocco show the crucial shift to columnar limbs and a fully quadrupedal stance. By the Middle Jurassic, Cetiosaurus in England, Patagosaurus in Argentina, and Shunosaurus in China hint at the direction the lineage would take by the late Jurassic, when necks became living cranes and bodies became mobile hillsides. The key was respiration and engineering. Air sacs invaded the vertebrae and lightened the skeleton while moving air through the lungs without the stop and start of mammalian breathing. The stomach could house fermenting microbes that unlocked calories from tough conifer needles and cycad fronds. A long neck let a browsing animal sweep a large circle without walking, conserving energy and heat. Gastroliths in some skeletons show that stones were swallowed to help grind plant matter, a digestive mill where true chewing was weak or absent. Ornithischians began modestly and spread quietly but decisively. Lesothosaurus in southern Africa was a nimble, small herbivore built for speed. Heterodontosaurus grew caniniform teeth at the front and battery-like cheek teeth at the back, a combination that hints at social display and at powerful chewing of fibrous plants. Scutellosaurus in the American Southwest carried small bony plates embedded in the skin, the earliest hint of the heavy armor that would later define stegosaurs and ankylosaurs. These early forms browsed beneath conifers and bennettitalian shrubs and left behind coprolites with shredded plant tissue and pollen that matched the gymnosperm-dominated floras of the time. The plant world that fed the dinosaurs was robust and layered. Conifers in several families sheltered entire communities and dropped cones that fed insects and small vertebrates. Ginkgo relatives fanned fans of leaves in streamside belts. Bennettitalians and cycads stood like living sculptures in open woodlands. Ferns draped moist hollows and recolonized ground after fires and floods. Pollen and spore records show clear climate zones. Cherulepidation conifers favored dry and salty lowlands and left clouds of distinctive pollen. Podocarps preferred cooler or wetter belts. The recurring signature of charcoal tells us that lightning and dry seasons still collaborated to set the ground alight. Many plant groups were adapted to that pulse. Thick bark and cones that opened after heat are ancient strategies that predate flowering plants. The air belonged to pterosaurs long before birds learned to fly. Early Jurassic forms with long tails and broad wings hunted fish above lagoons and insects above coastal plains. Delicate bones and fine joint surfaces speak of precise control in the air. Fossils from the Solnhofen limestone would later capture late Jurassic pterosaurs in astonishing detail. But even in older rocks, the posture is clear. A powerful shoulder, a long fourth finger, and a wing membrane that attached to the hind limb created a flight stroke unlike that of birds. Small pterosaurs likely hunted at twilight when the air is calm and insects are abundant. Larger forms patrolled cliffs and outer lagoons. Their presence altered the behavior of shoreline animals and likely added pressure to fish communities already preyed upon by marine reptiles. Mammals, though small, were not minor. Jurassic mammalia forms and true mammals appear in several lands at this time. Morganucodon scurried along riverbanks in Wales and China and took insects by night. Cynoconodon and other early forms wore precise molars that could shear and crush with surprising effectiveness. Docodonts crafted complicated teeth and later produced semi-aquatic forms such as Castorocauda that fished in streams and carried fur, a discovery that has given us the first direct evidence for hair in the Jurassic mammal record. Some Harameodon relatives evolved membranes for gliding across short gaps, a nocturnal partnership of claws, patagia, and large eyes. The basic mammalian solutions were in place. Warm blood, parental care, vibrissae, and acute hearing created a parallel story of success that ran beneath dinosaur feet for the rest of the Mesozoic. The seas responded to extinction with invention. Ichthyosaurs accelerated into the New Age with streamlined bodies and huge eyes for hunting in the dim blue. Temnodontosaurus reached lengths over 10 meters and hunted large prey, while Stenopterygius bore live young tail first in sheltered bays, a birth posture known from exquisitely preserved specimens in Germany. Plesiosaurs diversified into long-necked fishers and short-necked ambush hunters with broad skulls and power strokes like underwater flight. Early marine crocodile relatives explored coastal waters and would later commit fully to life at sea. Ammonites radiated into an astonishing variety of coiled forms and became the chronometers of Jurassic time. Belemnites, squid-like animals with bullet-shaped guards, filled schools in mid-water. Reef ecosystems recovered as scleractinian corals rebuilt limestone scaffolds in clear, warm shallows where currents and sunlight were right. The ocean did not remain stable. Around 183 million years ago, a pulse of volcanism linked to the Karoo and Farrar provinces coincided with the Torsian oceanic anoxic event. Black shales spread in Europe and beyond, and many marine groups turned over. After this disturbance, diversity climbed again on a new base. Evidence for social life and care appears in stone with a clarity that can be moving. In the early Jurassic of South Africa, Massospondylus nests hold eggs arrayed in neat circles and tiny hatchlings preserved near the rim, a picture of repeated nesting and possible caretaking at a communal site. Bone beds of Coelophysis in New Mexico and of other early dinosaurs show groups of similar-sized individuals that may have hunted or traveled together before flood or drought sealed their fate. Trackways along rifts sometimes preserve parallel paths of animals that walk together for some distance. These lines of footprints do not prove complex social structure, but they suggest that at least some dinosaurs sensed advantage in company or shared routes along the edges of lakes. The physiology behind this spread is written in both bone and rock. Dinosaurs commonly grew fibrolamellar bone, a tissue built fast and suffused with blood vessels. Growth rings show pauses in hard seasons and fast resumes when food returned, a tempo that fits a monsoonal world. Their air sac systems lightened bodies and cooled interiors by moving large volumes of air. Their eggs were numerous and nests often shallow and simple, a strategy that produces many hatchlings and spreads risk. The design choices are consistent across continents. When a group of animals with these traits encounters a world of open niches and seasonal stress, it tends to prosper. By the close of the Middle Jurassic, the identity of the age is unmistakable. Theropods ranged from small, swift insect eaters to large, bone-shearing predators. Sauropods grew tall and deep-chested and began to dominate the biomass of many inland plains. Ornithischians diversified into fast runners and into forms with armor and complex jaws for grinding. Pterosaurs owned the skies. Mammals owned the night and the narrow crevices. Marine reptiles ruled near shore and offshore waters. Plant communities were thick and spatially structured and sent waves of pollen across seasonal winds. The earth was warm, the poles were forested, and the continents still spoke with one voice even as rifts quietly widened. The age of dinosaurs was not a single invention. It was a set of successful answers to a planet that was large, seasonal, and often hot. The supercontinent did not fail in a single crack. It loosened in stages, like a grand mosaic that first hums with subtle strain and then parts along old seams. In the late Triassic, the earliest rifts opened as long linear valleys that filled with lakes and red sands. By the early Jurassic, those rifts linked into a young ocean. Basalt flooded valley floors and cooled into black steppes. The Palisades of the Hudson are the frozen throat of one such magma body that forced its way into rift sediments while the Central Atlantic magmatic province poured out on the surface. Between these fiery intervals lay long, quiet pauses in which mud settled into paper-thin laminae in rift lakes from Nova Scotia to Morocco. Every pair of laminae marks a year. Bundles of pairs wax and wane with the slow beat of Earth's orbit. The Newark Basin and its sister valleys are therefore not only the first scar of a new ocean, they are also a calendar that counts the pacing of the split. As the rifts deepened, seawater advanced along them, and the first Atlantic basins were born. Along the new margins, enormous blankets of salt precipitated where restricted arms of the sea evaporated beneath a hot sky. In the Gulf of Mexico, the Luan salt spread across the floor of a Jurassic basin that had only just opened between North America and Yucatan. Later, sediments would slide and fold over that soft layer and raise salt domes that pierce younger rocks. Farther east, along the central Atlantic margin, thick packages of evaporites and carbonates record a similar alternation of flooding and isolation as the ocean widened from a chain of gulfs into a continuous seaway. The crust beneath these basins shows the anatomy of birth. At depth, gabbro and sheeted dikes cooled within the ridge. Above, submarine lava built piles of pillow basalt as magma met water. Magnetic minerals in the basalt froze in step with the field of the day. As the field reversed polarity over time, those minerals recorded stripes. When mapped across the floor of the Atlantic, the stripes are mirror images that frame the mid-Atlantic ridge and prove that new crust has been added symmetrically for millions of years. The breakup moved south and east as well. Gondwana began to unravel along lines that would eventually separate Africa from Antarctica, and later Africa from South America. In the Jurassic, many of these were still rifts and narrow seas. The Great Opening of the South Atlantic is a story of the early Cretaceous, but its preface lies in Jurassic faulting and volcanism that weakened the continent along future coasts. The Tethys widened at the same time. It had been an embayment along the eastern flank of Pangaea. In the Jurassic, it matured into a true ocean that wound between Africa, India, and Eurasia. Fragments of former continental margins traveled into it as microcontinents and arcs. Where later mountain belts now rise in the Mediterranean and the Middle East, the Jurassic map carried shelves fed by rivers and lined with reefs. Pieces of the Tethyan floor would eventually be raised as ophiolites on land when those oceans closed. But in the Jurassic, they lay in place beneath clear tropical water, while ammonites coursed above them. The climate felt the geography change. A single supercontinent invites strong monsoons and a harsh interior. A coast-rich world invites softening winds and moisture to travel inland. As the Atlantic widened and the Tethys deepened, shorelines multiplied. Warm currents carried water along new paths. The long equatorial belt of the Tethys became a highway for heat, joining the tropical West Pacific to the young Atlantic. The result in many regions was a weakening of the old Pangaean monsoon and a shift toward more even rainfall on seasonal schedules. Deserts did not vanish, but they retreated from some interiors and became punctuated by belts of woodland and wetland. In mid-latitudes, temperate forests flourished on soils fed by volcanic ash and renewed by frequent fires. At high latitudes, warmth supported conifer woodlands and hardy ferns within reach of the polar circle. Fossil wood with annual rings records climates that were seasonal yet mild for long stretches of the Jurassic. The oceans reorganized as new gateways opened, with more margin length, upwelling zones multiplied and fertilized surface waters. Pelagic life responded with innovation. Calcareous nanoplankton evolved intricate plates that now rain to the deep sea as chalky snow. By the later Jurassic and Cretaceous, these coccolithophores would blanket ocean floors with white ooze. But the evolutionary hinge begins here. Planktonic foraminifera began to fill the midwater with floating shells that would also become carbon carriers to the depths. This shift in the producers that build calcium carbonate changed the carbon cycle. Carbon burial moved off the shelf and into abyssal plains, which allowed continents to store less limestone in shallow seas and left a record of chalk and marl on the deep ocean floor. In coastal and shelf settings, scleractinian corals returned to build reefs that curved in long arcs along the Tethys and along the young Atlantic. Their alliances with symbiotic algae allowed fast growth in clear, warm water and created habitats that supported sponges, mollusks, and fishes that hid and hunted within the reef framework. On land, the proliferation of coastlines produced biogeographic provinces. When Pangaea stood unbroken, animals could in principle disperse across vast ranges. As seaways grew and mountain belts rose, faunas became more regional. By the late Jurassic, community character in North America's Morrison Formation differed from that in the Portuguese Lourinhã beds and from that in the Tendaguru of Tanzania. All hosted herds of long-necked sauropods and strong-jawed theropods, but the caste lists diverged. Allosaurus and Diplodocus paced the Morrison floodplains. Torvosaurus and Lurinosaurus did the work in Iberia. Giraffatitan and Kentrosaurus flourished on East African coastal plains. Seeds and pollen tell a parallel story. Certain conifers preferred coastal belts swept by humid winds. Others favored uplands and drier interiors. The growing separation of landmasses nudged evolution along different paths, while keeping the overall Mesozoic pattern of conifer forests, cycad shrubs, ginkgo glades, and fern carpets intact. Rising seas amplified these differences. The Jurassic hosted episodic high stands when shallow epicontinental seas flooded broad lowlands. In North America, the Sundance Sea reached south from the Arctic, across what is now Wyoming and Montana, and left marine sands and shales interlayered with dinosaur-bearing river deposits. Farther east, the young Atlantic sent fingers of salt water into bays and estuaries, where stromatolites, oysters, and mangroves assembled communities tolerant of brackish conditions. Each transgression and retreat rearranged habitats and opened corridors for migration. Marine predators followed the water inland and withdrew as seas fell, leaving behind bone beds of ichthyosaurs and plesiosaurs that stranded in drying embayments. On shore, river systems adjusted their courses to new base levels, and floodplains shifted. The creatures that prospered were those that could track change or that were anchored to refuges that remained wet or wooded through the cycle. The deep earth persisted as an engine. As the lithosphere thinned above rising asthenosphere in rifts, heat flow increased and basins subsided, creating accommodation for thick sedimentary piles. Volcanic episodes such as the Karoo and Farrar provinces added carbon dioxide to the air and occasionally tipped the ocean into low oxygen states, as during the Torsian event when black shales spread across Europe and North Africa. Weathering of vast fresh basalt surfaces then drew carbon dioxide down and pulled climate back toward equilibrium. The seesaw is visible in the chemistry of marine carbonates and in the organic richness of the shales. It is also visible in fossils. Warm intervals favored coral belts that climbed poleward and favored ichthyosaurs that hunted in broad ranges. Cooler or more eutrophic intervals stressed those same communities and allowed other clades to step in. Even the shape of continental margins born in this time would echo forward into the human present. River deltas built great wedges of sand and mud into new oceans. Salt that had formed early in restricted basins flowed slowly under its own weight and created ridges and domes. Later, sediment draped those forms and sometimes sealed rising oil and gas. The North Sea basins and the Gulf of Mexico built energy stores from these layered processes. That story belongs to a much later chapter of Earth history, but the template was cut in the Jurassic when Pangaea began to fail. To watch the shattering of Pangaea is therefore to watch many systems reorganize at once. Tectonics tore continents free and created new crust. Ocean circulation rethreaded its currents through fresh gateways. Climates softened in many places as coastlines multiplied and monsoons weakened. Plants capitalized on new rainfall patterns and built forests along rivers that now ran to different seas. Animals tracked these changes and diversified into provinces shaped by land and water. The outcome was not simply a new map, it was a new set of rules for how heat and moisture moved and how life could ride those flows. By the end of the Jurassic, the unity of Pangaea was only a memory inscribed in matching rocks and fossils on opposite shores. In its place stood continents on their own journeys, separated by oceans that carried plankton snow to the deep and rimmed by reefs that shone in clear water. By the Middle and Late Jurassic, the planet had fully settled into its new pattern of seas and continents. The Atlantic was a young but real ocean. The Tethys had become a warm beltway for water and heat, and coastlines multiplied in a way that softened interiors and fed rains along river corridors. Into this geography, dinosaurs spread with a confidence that makes their trackways feel like signatures. Their prints stride across tidal flats in Portugal, across lake shores in eastern North America, and across floodplains in Tanzania and China. The variety of those tracks reveals slim three-toed hunters, broad four-footed giants, and herds that moved together long enough to leave parallel paths. The map was no longer a single continent, but dinosaurs treated it as a connected world, with related faunas on lands now far apart. The Morrison Formation of western North America is a good place to start. It stretches from New Mexico through Utah and Colorado into Wyoming and Montana. The rocks are stacked river deposits, floodplain muds, and the occasional lake bed. A record of seasonal rains followed by long dry spells. Quarries along its outcrops have yielded entire communities. There are towering sauropods such as Diplodocus and Apatosaurus with necks that swept broad arcs over conifer crowns, and heavier shouldered forms such as Camarasaurus that browsed at different heights. There are theropod predators, including Allosaurus, with a skull built to deliver powerful bites and to resist twisting forces when it tore flesh from bone. There are medium herbivores such as Dryosaurus, nimble and likely wary, and armored forms such as Stegosaurus with plates and spikes that have provoked a century of debate about display, defense, and heat exchange. The scene is familiar because it is well studied, but it is not unique. The Larinhan deposits in Portugal and the Tendaguru beds in Tanzania tell parallel stories with different casts. Torvosaurus and Luranosaurus in Iberia, and Giraffatitan and Kentrosaurus in East Africa fill roles comparable to the American giants, but speak with local accents of bone and tooth. The reason this world cohered is written in physiology and growth. Dinosaurs grew fibrolamellar bone, a tissue that forms quickly and is threaded with blood vessels. It is the bone of fast-growing animals. Growth rings in many species record pauses during hard seasons and resumptions when food returned, a tempo that suits monsoon climates. Air sacs invaded the vertebrae and lightened the skeleton, while lungs likely moved air in a single direction through rigid tubes that allowed efficient extraction of oxygen. That airflow pattern is found in modern birds and has been detected in living crocodilians, which suggests a deep origin within archosaurs. Together with an upright posture and long efficient strides, these traits gave dinosaurs the endurance to cover ground, to feed for long hours, and to keep their cores cool under a strong Sunday. Sauropods turned that engineering into a novel solution for feeding. Their necks let them harvest leaves across a wide circle without moving their heavy bodies. Pneumatic air spaces in their vertebrae reduced weight without sacrificing strength. Their digestive strategy likely relied on large vats filled with microbes that fermented tough plant matter into usable calories. Some carried stones in their stomachs that helped grind food. Their footprints formed trackways of regular spacing that look like the metronome of a deliberate walk. In some places, those trackways cross shallow rivers, and the impressions of hand and foot tell us about weight distribution and posture in water. The sheer biomass of sauropods in many late Jurassic ecosystems implies that river corridors and floodplains supported wide belts of vegetation, and that fire and flood created mosaics of young and older growth. Plants were mostly gymnosperms. Conifers towered over cycads and bonetitalians, while ginkgo relatives fanned broad leaves along river margins. Ferns recolonized after floods and built green carpets in shade. Theropods filled the roles of large and small predators. Allosaurus had recurved teeth with serrated edges and a skull that could absorb and redirect stress as it fed. Torvosaurus and other large carnivores matched that plan with their own variations. Smaller forms such as Ornitholestes and Compsognathus took on quick prey and scavenged. In China, richly preserved beds of the Tiaojishan and Yixian regions show that many theropods carried feathers. Anchionis and Xiaotingia, among others, preserve feathered bodies, complex wings, and long feathers on the legs that may have aided in maneuvering. These fossils fix feathers as a deep feature of the theropod line and blur the boundary between small predatory dinosaurs and early birds. The wishbone sits in their chests, the semilunate wrist bone that allows a wing beat sits in their hands, and the tail shortens and stiffens in forms close to flight. The Solnhofen lagoons of Germany add another piece. There, Archaeopteryx lies in fine limestone with a halo of feathers, a long bony tail, and teeth in the jaws. It could climb and glide and probably fly in short flapping bursts across quiet lagoons. It was a bridge rather than a destination, but it stands as a landmark that the sky was now part of the dinosaur story. Ornithischians diversified into creative herbivores. Heterodontosaurus carried a mix of small tusk-like teeth in front and grinding teeth in the back, and may have used its front teeth in display or in intraspecific combat. Lesothosaurus was a small fleet plant eater that probably relied on speed and awareness. Scutellosaurus wore small plates embedded in the skin, a hint of defenses that would later blossom into full armor. By late Jurassic time, the first true stegosaurs and ankylosaurs had taken shape. The plates of Stegosaurus were thin and crossed by blood vessel grooves, which suggests roles in display and perhaps limited heat exchange. Its tail spikes are placed and built for use. When we find healed injuries on the bones of predators that match the spacing of those spikes, it suggests that the defensive story is not only plausible but documented. The air above this world belonged to pterosaurs. Early Jurassic forms had long tails and simple teeth suited for insects and small fish. By late Jurassic time, pterosaurs had diversified into fishers, crab catchers, and generalists. Rhamphorhynchus from Solnhofen had long, narrow jaws lined with interlocking teeth and a tail vein that likely improved stability. Pterodactylus had a shorter tail and a long fourth finger that supported a wing membrane anchored to the hind limb. Fine impressions preserve the fibers that stiffened those membranes and the soft tissue crest that trimmed the head in some species. The presence of pycnofibers, a coat of hair like filaments, points to insulation and to high aerobic ability. Their breeding and nesting behaviors remain partly hidden, but bone chemistry and growth suggest that many pterosaurs grew fast and were capable flyers not long after hatching. Mammals remained small in body size, but not small in ecological ambition. Docodonts crafted complex molars with basins and ridges that fit together like machine parts, which allowed shearing and grinding. Castorrhocorda from the Middle Jurassic of China carried fur, had a flattened tail, and likely hunted in streams, a combination that shows mammals experimenting with aquatic life far earlier than once thought. Early relatives of multituberculates bore multiple longitudinal cusps on their teeth and climbed with grasping feet, a recipe for life on trunks and branches. Nocturnality was common, and with it came enlarged eyes and refined hearing. The middle ear bones in early mammals evolved from jaw elements and improved sensitivity to high frequencies, an advantage in the dark when rustles and chirps carry crucial information. The seas of the Jurassic completed the circle. Marine reptiles refined the art of swimming. Ichthyosaurs became streamlined and fast. Temnodontosaurus grew large eyes and hunted in deeper light, while Ophthalmosaurus took that adaptation to an extreme. Plesiosaurs split into long-necked forms such as Cryptoclydus that snatched small fish with fine teeth, and short-necked pliosaurs with massive heads and jaws that could crush large prey. Thalattosuchian crocodile relatives such as Metriorhynchus left the shore entirely. Their limbs became paddles, their tails bore fins, and their bodies lost heavy armor to become more buoyant and faster in open water. Ammonites filled the water column with a taxonomic fireworks of shell forms and sutures. Belemnites cruised as bullet-shaped guards in the mantle of squid-like hunters. Reef belts built by scleractinian corals returned to strength and curved around the margins of the Tethys and the young Atlantic, creating long chains of habitat that fostered diversity and protected coastlines from storm energy. Climate through much of the Jurassic was warm and equable, with forested poles during intervals when ice was absent. The carbon cycle breathed in response to volcanism and weathering. The Taussian oceanic anoxic event in the early Jurassic marked a brief time when black shales spread widely and marine turnovers occurred, likely driven by a pulse of volcanic carbon paired with nutrient delivery that fertilized surface waters. Afterward, diversity rebuilt on a changed base of phytoplankton and reef architects. On land, fire was a regular part of many ecosystems. Charcoal fragments are common in Jurassic sediments. Plants carried adaptations to fire such as thick bark and cones that open after heat. The patchwork produced by burn and regrowth created edges and clearings that favored fast-growing shrubs and the animals that browsed them. Behavior adds texture to this world. Massospondylus nests in South Africa reveal repeated use of nesting sites and arrangement of eggs in rings, which hints at parental organization. Bone beds of Coelophysis in New Mexico and of other theropods, record groups that died together, perhaps when drought focused animals at a shrinking waterhole and a sudden flood buried them. Sauropod tracks in Portugal and Wyoming show multiple individuals moving in the same direction at similar speeds, possibly family groups or loose herds following a river course. Tooth marks on bones match the spacing and shape of theropod teeth and suggest that carcasses were revisited over days and weeks, and that feeding was social at least, in the sense that multiple animals fed sequentially at a site. The world of dinosaurs in the Jurassic is therefore a complete working planet. Rivers and monsoons drive a seasonal pump. Plants build architecture for energy capture and soils for storage. Insects pollinate gymnosperms where wind does not suffice and recycle litter when storms strip branches. Dinosaurs partition the terrestrial space from canopy height to ground layer and from river margin to dune. Pterosaurs own the sky and play by the rules of air. Mammals own the night and the narrow refuges that large bodies cannot reach. The seas are no less full. Reptiles rule the open blue. Invertebrates write the chronicle of time in coiled shells. And reefs return as bright cities along clear coasts. The continents no longer speak as one, yet common solutions evolve again and again on different shores. It is a world that hums with repetition and with variation, and that feels stable enough to last forever. It did not. The next acts will continue the continental drift, will bring flowering plants into the picture, and will test dinosaurs with new climate beats. For the moment, in the long sun of the late Jurassic, the age of dinosaurs is not a slogan. It is the daily fact of earth and air and water. The proof that the continents were once one body is everywhere if you know where to look. It is carved into mountain belts that begin on one shore and finish on another. It lies inside pebbles dropped by ancient glaciers that scratched their way across Gondwana and left grooves that point toward a single southern ice center. It rides on the backs of fossils that never learned to swim across oceans yet somehow appear on both sides of the Atlantic. It hides in minerals that cooled from lava and froze tiny compasses in place, so that when we turn continents back like pieces of a patient puzzle, the magnetized grains point toward the same past pole. The modern world is a collection of rafts. Each raft carries archives of a time when the rafts were one island called Pangaea. Start with the mountains. The Appalachians of North America line up with the Caledonian and Variscan belts that arc through Ireland, Scotland, Scandinavia, and Central Europe, and continue into the anti-Atlas of Morocco. Their rocks share the same ages and the same scars. They hold slivers of ancient ocean crust caught in the collision, high-pressure metamorphic minerals grown deep within a squeezed boundary, and granites that cooled from the last magmas that rose during suturing. Farther east, the Ural Mountains preserve the seam where East European land welded to blocks near Siberia. These belts are not random ridges. They are stitches that once held the supercontinent together. Fossils turn stitches into straight talk. Mesosaurus was a small reptile that lived in fresh water. It is found only in Permian rocks of Brazil and Namibia. Glossopteris was a seed fern with tongue-shaped leaves that blanketed Gondwana from India to South Africa to Australia and left thick beds of leaves and wood in the Permian. Synagnothus and Lystrosaurus were land animals whose bones lie in matching Triassic layers across southern Pangaea. None of these animals could cross a deep, salty ocean or fly coast to coast. They did not have to. At the time of their lives, there was no ocean between those lands. There was only a continuous surface on which they walked and fed and died. Climate left its own signature. In rocks of similar age across South America, Southern Africa, India, and Australia, there are pavements scratched by glacial ice that once flowed across a united Gondwana. The scratches point toward an ice cap centered on the former South Polar region. Dropstones that fell from floating ice into marine muds are found across these same southern lands. In some paleosols, the microscopic pores of plant leaves are preserved. Count the stomata, and you can infer the proportion of carbon dioxide in the air that washed over those leaves. Those numbers change through the late Paleozoic and early Mesozoic in ways that align with the waxing and waning of ice and with the building and breaking of the supercontinent. In shallow seas, where reefs once grew, there are gaps and muds that speak of heat and oxygen loss during crises. And after the crises, there are microbial mats that spread where grazers once grazed, a quiet index of ecosystems trying to start again. There were clever minds who listened to these clues before the age of satellites. In the early 20th century, Alfred Wegener argued that continents drifted. He gathered the fit of shorelines, the alignment of mountain belts, the distribution of fossils, and the shared glacial record into a case that was bold and wrong in mechanism, but right in conclusion. The physics came later. Mid-century geophysicists mapped magnetic stripes on the floor of the New Atlantic and showed that ocean crust is born at the mid-ocean ridge and moves aside in both directions. Earth scientists measured heat flow and found a warm spine along that ridge and cooler crust away from it. Seismologists triangulated earthquakes and traced lines that mark trenches where ocean crust sinks. Geodesists now watch continents slide on the surface in real time using satellites. The modern picture is not a speculation, but a measured fact. Plates move because Earth cools and the mantle convects, because ridges push and slabs pull, and because the lithosphere is strong enough to carry continents like boats on a slow-moving sea. The breakup of Pangaea wrote new laws for climate and life that still govern the present. A single supercontinent invites strong monsoons and deserts in the interior. Many coasts invite moderated seasons and moisture that reaches deep inland. When the Atlantic opened and the Tethys widened, shorelines multiplied and the old Pangaean monsoon weakened. Ocean currents found new paths. Heat flowed along the Tethyan belt and later along the tropical Atlantic, softening climates on several continents. Upwelling zones increased along young margins and fertilized surface waters. New plankton evolved with calcium carbonate plates and shells that rained to the deep as white snow and built thick chalks across the ocean floor. When you stand on the white cliffs of southern England, you stand on the changed carbon cycle of a world with new oceans. When you turn your face into the wind on a reef in the Caribbean, you feel the function of a tropical current born when Pangaea failed. Modern landscapes and resources carry this memory. Early Atlantic basins hosted restricted seas where salt precipitated in thick blankets. The salt flowed like cold wax in the subsurface and rose into domes that later trapped oil and gas in the Gulf of Mexico and beneath the North Sea. Reef belts that grew along Jurassic and Cretaceous shelves banked limestones that became aquifers and stores of carbon. Organic rich shales deposited during oxygen-poor intervals became source rocks that now power cities. The Permian Basin of Texas is framed by a fossil reef that rimmed a restricted sea in late Permian time. Its hydrocarbons were born from muds that settled in that quiet basin. The distribution of metals also remembers Pangaea. Volcanic arcs that rimmed the supercontinent and later oceans concentrated copper and gold. Coal measures in the Karoo of Africa and in the Sydney Basin of Australia record the persistence of Gondwanan wetlands into the Permian and Triassic. To light a lamp or turn a key in many modern places is to draw down energy that was organized by the geography that Pangaea set in place. Biology carries the same map. The pattern of modern faunas and floras reads like a set of postcards from a broken supercontinent. Ratite birds on far continents share a common Gondwanan story and then diverge along separate paths. Southern beaches grow in South America, New Zealand, and Australia, and record an ancient link even as they tell a tale of later dispersal by seed and wind. Lungfish persist in Africa, South America, and Australia as living witnesses to a very old distribution that formed when these lands were one. Marsupials once ranged widely across Gondwana. Their present concentration in Australia and nearby islands is a narrowed echo that still points toward a time when corridors stretched from Antarctica into lands that were not yet isolated by southern ocean currents. Even the distribution of crocodilians along tropical coasts and rivers traces the warm margins of the Tethys and the young Atlantic that became their highways. The legacy of Pangaea also includes what came after. India drifted away from Gondwana across the Tethys and collided with Asia. The Himalaya and the Tibetan Plateau rose where the ocean disappeared and the crust stacked itself into a roof of the world. Their uplift altered winds and monsoons for half the planet and drew carbon dioxide from the air as new rock weathered under monsoon rains. Far from Asia, Africa has pressed against Europe in pulses that built the Alps and the Carpathians and wrinkled the Mediterranean into a patchwork of small basins and ridges. Pieces of the Tethys seafloor have been carried up and placed on land as ophiolites in Oman, Cyprus, and Greece. In those ophiolites, a person can walk from deep mantle rocks through gabbro chambers and upsheeted dikes to pillow lavas of an ancient ocean floor in a single day. That walk is a gift from a vanished sea that once lapped the shores of Pangaea. If Pangaea is a memory, it is also a pattern. Supercontinents have come together before and will again. Rodinia gathered in the Proterozoic and broke apart long before animals evolved skeletons. Pangaea may have followed as a brief union. Pangaea was the latest and most famous because its story overlaps ours. The physics that drove these cycles have not retired. The Atlantic still widens along its ridge. The Pacific is ringed by trenches that are consuming old ocean floor. The Red Sea and the Gulf of Aden stretch as young oceans in the making. The East African Rift is a place where a continent begins to part, and where lakes that fill long, narrow valleys carry valves that count seasons as earlier rift lakes did along the newborn Atlantic. Some geodynamic models foresee a future in which the Americas close on Asia and a new supercontinent forms around the Arctic. Others imagine Africa continuing north and closing the Mediterranean to build a new center of high ground. Whatever the exact map, the cycle will continue because Earth cools and moves heat by moving its outer shell. From Pangaea, we learned how a planet breathes. When continents gather, mountain belts rise and expose fresh rock that consumes carbon dioxide as it weathers. Interiors dry and fires become common as vegetation adapts to long seasonal extremes. When continents part, greenhouse gases from rifts warm the air, and then weathering of fresh basalt draws it down. New coastlines invite rains, inland and rivers build layered stories of flood and meander. Ocean gateways open and close, and the circulation machine switches routes. At times of stress, such as the end Permian, we learn that a flood of volcanic gases can push the system into a state with hot oceans starved of oxygen and with disrupted food webs. We learn that recovery can be slow, that it can take millions of years to rebuild complexity. We also learn that survivors reshape the rules. The Triassic and Jurassic were not copies of the Permian. They were fresh chapters that would never have been written without the purge and the geography that followed. The scale of the lesson is large, but it reaches down into detail. Detrital zircon grains carried by rivers into sandstones retain the age of the rocks from which they eroded. Sand from the Appalachians and from the Anti-Atlas can be matched by age signatures across the Atlantic, a mineral handshake across time. Blueschist and eclogite preserve the cold, high-pressure history of subduction beneath Pangaea and speak to the depth of burial and the path back to daylight. Malangis of broken rock and exotic blocks along sutures read like jumbled diaries of the hours when oceans closed. In the deep mantle beneath the former center of Pangaea, seismic tomography images slabs that fell long ago and hot regions that may be the roots of superplumes that help drive both assembly and breakup. The planet remembers not only in crust, but in the slow lofts and dives of rock below our feet. We live with practical consequences of these echoes every day. The broad, low slopes and shelves along passive margins became home to cities and ports. The stubborn bedrock ridges of old origins turn rivers aside and shape valleys and roads. Soil fertility follows the parent rock and the ash of former volcanoes. The groundwater that fills limestone aquifers and the springs that issue from their edges belong to the carbonates laid down when Tethyan shelves were bright with reefs. The hazard of earthquakes and volcanoes maps the living edges of plates and the trenches where ocean floor sinks. But even far from those edges, old faults under former rifts can wake and remind us that no region is forever quiet. Pangaea's last message is an invitation to think in scales that include us and also ignore us. The supercontinent stage organized almost every aspect of the surface environment. It set where rain fell and where deserts slept. It channeled currents and built gateways that moved heat. It gathered life, pruned it, and asked it to try again with new tools. The evidence that allows us to tell that story is humble and precise. It is a fern leaf turned to coal, a thin band of salt in a core from the deep, a dinosaur track pressed into wet sand that dried in the sun, a crystal that carries the age of a mountain like a number on a passport. When we assemble those pieces, the picture that emerges explains the present and makes the future less mysterious.